Is everybody here? Cold? Directly to you. It's probably just getting the fan a little bit upper. All right, I think it's about time to start. Good morning, everyone. I hope you guys rested. I hope you didn't stay the whole night just solving a small problem in here. What I'm going to do with that problem, we were just talking about that I needed to evaluate you at the end, or by tomorrow, right? We got a test. So whatever you did in here is going to be some mark for that final, okay, for the final thing. Whatever it is you did, the effort, to try it. So what I'm going to be collecting is probably the table. If you can just put your name on it, right? If more of one word together, please put the two names in there and just handle them to me by the end of the day, okay? So that tomorrow we're going to have the composite results in here, and we're just going to see what happened, all right? So that's going to be part of your evaluation, and this just evaluation, effort. All right. Do you guys have any questions in here? Okay. What we're going to be looking at today is we're going to switch gears from C-pitch analysis to the shear strength analysis, right? Shear strength also is a very important area in which geotechnical engineering and pavement engineering we're going to need to be very expert on it. And I'm going to try to do again what I did on the C-pitch analysis. We're going to try to get the basics to you for you to understand why we use this equation, and see at the end a couple of examples of how we can use, okay, these equations. These concepts, I will say. All right. So we're going to talk a little bit about the stress state variables that are responsible of the shear strength behavior of the soils, of the unsaturated soils, and I've been already talked about that briefly. And then we're going to talk about the shear strength of unsaturated soil, the equations that are available, how do you measure, and again, how you can estimate it, right, if you don't have access to measure it directly, right? So this is the way we're doing today again. So we're going to start with the stress state for the saturated soils, which is, you're familiar with that. So you're going to see that how this one is a special case of the unsaturated case, actually, right? Instead of being the most important, the saturated case, the most important is your general equation, and then one of the conditions is when you, special cases when you have saturation equal to 100, pretty much, right? A brief history of how we measure this one and how these things start evolving, and I'm not going to show everything that everybody had done since the 60s, I guess. But I'm going to bring elements that they added to the theory that were very important at that point, right, for us to have whatever we have today. The shear strength equation for the unsaturated soils, how to determine that in the lab, and how to predict it if we don't have lab data. Okay. So back to Terzaghi. Carl Terzaghi is our father, the father of soil mechanics. Everybody knows and hear about Saul Terzaghi if you are in graduate school in geotechnical engineering. And he postulated his effective stress principle to describe the mechanical behavior of the saturated soils on shear, right? And this one is a very well-known equation, 1936 we're talking about, okay, almost 100 years. And this one is the effective stress equal to your total stress minus forward pressure. So that's how everything started. Like when he started putting equations to the solid mechanics, we became a mechanistic, group of people working, mechanistic engineering group. So what are the strengths of this? It's applicable to all sands, silts, and clays. It was good for that when you get into the saturated. There was independent of soil properties, so it became a constitutive, relation, not constitutive relationship. Constitutive is when we put the soil properties in there. But it was independent. There are the stress state variables. Remember, a stress state variable is a variable only if it's independent of the material properties. Okay? Only if it's independent of material properties. It's what you apply to the soil. The soil has no idea where it's coming. Okay? It's receiving something internally or externally, right? The environmental meson changes, and the suction is an internal stress that is changing, right? It's totally independent. Same thing for the normal stresses or the applied stresses external. So these are stress state variables, and can be applied independently in each Cartesian coordinate. All right. The disadvantage was too much emphasis placed on this equation, in such a way that the effective stress became the great deal for us, and we didn't do better than that. All right. So, and the source of effective stress was not known. We said, okay, we got total stress, forward pressure, but there was no studies about all of these internal forces that work together for the effective stress to go. Okay. So I'm going to go quickly on that one. You have the information. You already got the slides for this today? Okay. Thank you. A little bit quickly on that, but again, I just want you to understand, the evolution of that since the 1940s, when Bharat says, okay, he started with the theory of consolidation, and he said, okay, we got now occluded air bubbles. Okay, so you need to understand that the theories for continuum mechanics, you have to have continuous flow of water, continuous flow of air for that to work. When you start getting into the occluded thing, you're going to need to start working on discrete elements analysis, stuff like that, which is not the same. But nevertheless, he started with that, and he highlighted that there could be a separation between the total stress and the pore water pressure changes. Okay, and then Coleman suggested that you can start combining those stress states, sigma 1 and minus sigma pore air pressure, or sigma 1 minus pore water pressure, or sigma 3 minus pore air pressure, or pore water pressure minus pore air. So he tried all of these combinations, right? Because we needed something easy to measure for us in the laboratory, okay? And that was the idea of combining stuff so we could measure that, okay? And this one is the assumption that was used to start doing the constitutive relationship that we have. Then Bishop, that we saw the question that I don't like, okay? But Bishop did a great amount of work. I mean, he measured, he started putting together the testing. I mean, he postulated a lot of stuff on this unsaturated soil mechanics, 1963. He observed that when he started changing the moisture or the suction in the soil, changing the moisture, drying or wetting, the volume change behavior was different than putting a load on it. All right, so he said those two have to be independent stress state variable. You see the concept is pretty important on that regards, right? Then Matthias and Radhakrishna start introducing the concept of state parameters, right? And again, everything started with volume change behavior, and then we're just getting into the shear strain. I went a lot on this one, but okay. There were some other people that started working on that, and again, it appeared that the matrix suction, when we have it different from the net normal stress, was working very good, okay? And one after the other one, they were just publishing more and more on how if you divide those two variables, you will be able to, say how the soil will behave. And Friedland came in the 70s, which generated a theoretical equilibrium analysis for unsaturated soil elements, and that's the one I'm going to be quickly working on in here. And I say quickly, I'm trying to have as much as I can. But he considered the air phase, the water phase, the solids, and also that contractile skill that Professor Bharat talked the first day. The contractile skin is that, a skin between the water and the air, right? And basically, he also considered that in his equilibrium conditions. And he definitely, and he proved in several papers that the best combination was the net normal stress, the total minus pore air pressure, remember yesterday, and the suction, pore air minus pore water pressure. But they tried many combinations. I mean, it's just not just boom, it was years of information to get to that point. So two independent stress tensors containing the stress state variables form the fundamental basis for developing a science for unsaturated soil mechanics. So that's how it started and how it was evolved. And I didn't include many of the people that contributed to that. So we start now getting to the effective stress equations, all right? So 1958, Crony started with the effective stress equation again, and he started putting a parameter, right, beta prime, right, to the pore water pressure. He said, okay, if I just vary that beta prime, right, and just make this guy less, I'm going to have higher effective stress, which is what happens, right, when you dry your soil. You're going to have higher strength. So, and then Bishop came with the equation. This is the one that became very famous. Not only that, because he used the two stress variables were fundamental and were correct, but then his famous chi value that everybody adopted, right? Like good. But again, I want to show you these shortcomings for that equation. Then Richard, not the Richards from the Richards equation, he came with this kind of formulation when you have a chi m, which was the effective stress parameter for matrix suction. This is the matrix suction pore air, and this one is another effective stress parameter for the solute suction. Okay, just linked to the osmotic suction in that. Yes, in that case, this is the way he formulated. But it is the osmotic component, so he started adding that osmotic component in there, which is important for some applications. So Bishop equation, again, I just talk a lot about, but Blight is the one that convinced everybody, all the scientific community, 1 year later after the equation, that chi parameter was also a function of the degree of saturation. And if the degree of saturation was a function of suction, it was kind of a mess in there, right? A mess. In there, and they said, well, the results show for different compacted soil that there was also a scatter in the relationship between the chi and the degree of saturation, and everyone was independent of each other. So it wasn't a single value effective stress equation, which he critiqued at that time. So for the effective stress approach for unsaturated soils, up to that point, there were several equations that have omitted the effect of pore air pressure. If you didn't see, okay, they put in there, put atmospheric 0, and that's okay, what we do, but suction is a function of that, right, whether we put it at 0 or not. All the equations were constitutive in character, in that the soil properties were incorporated later to put the constitutive relationship, not part of the stress state or the stress variables. But all of them violated the fundamental principle of continuum mechanics. So in order to have a good solid stress state variables for unsaturated soils, these were the selection criteria that Friedland used for that. The variables can be experimentally tested, something that we cannot test as engineers. I'm not going to use that thing, okay? He said, we need that. Variables can be theoretically justified using equilibrium considerations, Okay, so we're going to have continuum mechanics applying to this one. Variables were the component stresses that can be measured in engineering practice, and variables that meet the requirements set out by the definition of state variables in continuum mechanics. Okay, it's something that you all the equilibrium considerations will apply. So what it was done, it was that the variables that they use, he said, okay, the stress state variables can be taken as, okay, first of all, it has to comply with the equilibrium of one phase, like the solid phase, for example. Remember continuum mechanics? Okay, I'm going to show you in a minute. And also, every one of those phases have to be at equilibrium. All right? Have to have an equilibrium condition. Water phase equilibrium, air phase equilibrium, and the contractile skill equilibrium. Okay, so this one was a fundamental thing for them to postulate that. And I'm just going to show you here. For example, this one is the equilibrium equation for the one-phase soil. Okay, and he said, okay, we do have two forces that are going to be there, obviously the body force and also the surface forces, right? This is what you've been learning for one element, you know, discrete element that will just get the continuum mechanics. And those stress vectors on the surface on a particular phase of the elements are the limiting values that you're going to have. So you're going to consider one of these elements, and whatever stresses you got, you know, are going to be an extra stress as you get out of the other phase, right? The delta. So they use a cube for a free body diagram, and basically representing the whole elemental volume of the soil. Okay. So what you got in here was, in every phase you're going to have the shearing stresses, right? And you're also going to have the normal stresses for that. And basically, he postulated, remember, it's just for the solid, right? No water, no air, nothing. All right? So just for the solids. So he formulated, based on conservation of linear momentum, the equation in one of the directions. This one is, for example, of the shearing stresses that you find, the normal stresses in here, the gravitational stress, and basically this one is an acceleration term, that if you assume no acceleration of the soil, that can be zero, right? This one is the acceleration, that's the velocity, and then you ended up with the stress tensor that you all know, right? You all know in the three-dimensional analysis. All right, so it's the same thing. So it applies for a saturated and unsaturated. Equilibrium in the solid phase must occur, right? And you have all these, subscripts depending on the direction of your. So it's a three-dimensional analysis. Then they went into the independent phase equilibrium. Okay, each phase in the solid structure is independent from one another. It's independent from one another, right? This is because each phase has its own independent properties. They're independent, they're linear, they're continuous and coincident. This is the whole postulation, right? So they have to be independent of each other. And then what we do is we use superposition, okay, on all this equilibrium analysis. So the areas or the volumes that are associated with each phase, what is done is being written down or related to the porosities, okay, to the porosities. So remember what the volume of voids is, when you do have the volume of voids, or when you have volume of water or volume of air, right? There are, porosities, right? Porosities within the soil, okay? So this is done by using the porosity designation for the volume. And let's, for example, in here, a water phase equilibrium analysis, in which you do have, in this case, again, you just said, okay, this thing is going to be saturated, all right? This is the water. That's the water equilibrium analysis. And this is the equilibrium continuum mechanics analysis. And basically, what they do is, okay, what is the interaction of the body forces between the solid and the water, okay? I only have water around it, okay? And basically they use an interaction force between those two, and then also use the continuum with the porosity, right? The porosity of the water times the gamma of the water, and going over the other side with the infinitesimal, change on that one, right? So you do the summation of equilibrium on the one direction. The interaction force between the water and solids is kind of a C-pitch force, and it's right here. And basically, this equation is the one that you use that will result in the effective stress equation. Total stress minus pore water pressure, right? That's basically the equation that you're going to be using for that. Same thing they did for the air. Okay, now you got a solid, the element of solid, and now it's interacting with air. And they did exactly the same, the equilibrium analysis for the air, okay? In this one, so basically they assumed that the solid was completely dry, two-dimensional phase system, solid and air only, and the equilibrium equation can be written for the air phase the same as the water phase. Probably you don't have that slices, right? Because I saw some were interested on this, and I add them at the end, so I don't know if you don't have them, I can just give it to you later on. Anyway, so just to show you the way that they were doing, this one. So they were equilibrium analysis. The contractile skin usually was taken as part of the solids, okay? That's one way of looking at that. There were some physics around that by several authors, but I think Fred Land got all this one and figured out that the interaction was, could be taken, the skin could be taken as part of the solid. Okay, so that's how he did that. But nevertheless, all this, okay, what is the contractile skin? Here is this. Okay, so that's influenced the solid structure by its ability to exert the tension between those. Professor Bharat already explained that to you. This is a wearable soil. That's the contractile skin. Is kind of concave for that. And when you have a repellent soil, the contractile skin is going to be kind of a convex, right? And then you're going to have that kind of stuff. In this case, for example, the pore pressure is greater than pore water pressure, so the suction is positive, right? Suction is positive. Then you're going to have this one going that way. The tension is going to go from the sides. And when the pore pressure is less than the pore water pressure, you kind of have, going on the other direction, right? So this one is also, there is an equilibrium condition for that between the air and the water, which is the skin, right, the contractile skin. Now forget about the solid, and now you got water and the air going on in there, right, between those two. And basically, a constant degree of saturation condition was maintained for the soil, while the flow of the air and the water in the soil were kept independent to each other. And basically, the unit surface tension magnitude that you have in there, the constant, was constant at a particular temperature. Based on all of these, they put them together, obviously, like, all the equilibrium together. Then they made the superposition by adding those equilibrium equations together. And they come up with this set of parameters. That's the one I showed you the first day in class. That basically, this one is just for a two-dimensional, but you can put it on the little cube. This is the complete form of the stress state at a point for an unsaturated soil in a two-dimensional basis. You're going to have the normal stress minus pore pressure, the shear stress is going on in there, the pore water pressure right there, and that's going to give you the whole, tensor. But this is how it is. It is pure continuum solid mechanics. Now, that doesn't mean that there are no other theories that will do that a different way and be okay, right? And just come out with something like that. But on continuum solid mechanics, that's the way they did it, all right? So, again, I want you to be aware that there are some other ways of doing business, right, in terms of physics. All right. So how we use that on the shear strength of unsaturated soil? Now you do have the independent stress state variable that we're going to work against or in favor of you for analyzing shear strength, all right? And again, you need to realize that you know what the pore area minus pore water pressure is the I guess the environmental load that you're going to have in there, right? It's going to be that. And this one is the normal stress is your external load, your building, your whatever it is, your confining pressure, same as you have done that before, and obviously the shear stresses, right? So this is what you got. So there are many problems, obviously, in engineering that you are very well versed on that you need the shear strength of the soils to solve them. Right? Bearing capacity is one of them for the foundations. Lateral air pressure is another one, and slope stability, right? I do have very good examples on bearing capacity and lateral pressure, but I thought the first day that we introduced everybody, whoever is very, very likely invested in slope stability, right? So I just brought my little example on slope stability here, right? So this lecture, or this part of the lecture, will describe how the shear strength of unsaturated soil can be formulated in terms of those stress state variables that I just presented, and the shear strength parameters for saturated soils. All right. So you need to realize that when we talk about K and SAT function, remember yesterday? That was a function of the soil water characteristic curve, right? Which is, the stress variable was there, the suction value, plus the saturated value, right? You needed to include that saturated value. This is nothing but, one corner that you need to fix, right, in order to do the whole function. Same thing in here. In order to do the whole shear strength, behavior, in terms of now we need two stress variables, not just one, right? In terms of net normal stress and the suction, we need to start with the saturated condition over the dry condition, right? So we need the saturated shear strength parameters, the C and the phi, or the C prime and phi prime that you've been working on since you start your graduate school or even before that, all right? So this is the shear strength for saturated soils. You all are very familiar with that. This is the case for one of the models of many, many models that are available. This one is the Moore-Coulomb failure envelope for a saturated soil. It's a criterion that was, that Terzaghi again, 1936, and it's a straight line pretty much, which is actually been killing us because everybody thinks it's true, right? That's not true if you have a very wide range of variability, right, on the lower side and the high side. Again, that will give you a couple of parameters in there, the intercept between the shear strength and the net normal and the normal stress. In this case, it's saturated, so it's going to be your effective stress, right? Because your pore area and pore water pressure will be the same, so it's the same thing in here. And the phi prime value, all right? It's a straight line again. I don't believe in cohesion either, right? For normally consolidated soil, for sandy materials, you have no cohesion. The only way that you start getting into an intercept in here is when you have over-consolidated soils around here, and all your more circles will accumulate in here. It's going to make something like that, right? It's a dense material on that stuff, right? So this equation defines a straight line, represents the number of possible combinations between the effective normal stress and the shear strength of the soil at the failure plane. And basically, pore water pressure acts equally all over the planes, on this, element that we show a little bit earlier. And the failure envelope is obtained by plotting the line tangent to a series of more circles, right, that you do for different stress conditions, right? The deviator stress in here, another deviator stress in here, you vary this one, and then you do your line. So this is the concept we use for shear strength for unsaturated soils, right? Two-dimensional, it could be three-dimensional. This one is sigma 1 minus sigma 3, but there is another one that is sigma 2 minus sigma 3, right? Sigma 2 minus sigma 1, I guess. For triaxial conditions will be the same. So we start with that, and then we start, okay, how we can translate this one into the unsaturated soil world, right? What we're going to be doing that. And in 1956, Donald started working on a direct shear testing, okay? And basically what he did is he got a shear box. He modified that. He put a membrane, a colloidal membrane, with, you know, like air entry values. Just think about that, right? Has an air entry value to that. And basically, he put that in there. The sample at the top was open to atmospheric pressure. So basically, he controlled the pore air pressure, right, to 0. On the top, it was open to the atmospheric pressure. And at the bottom of the sample, basically, he created some suction. He created some suction in here with this. And therefore, he imposed some suction in there, and he was measured that. How he imposed your suction? Well, you can use a manometer, you know, with some constant head overflow tube, and basically maintain any suction that you want to maintain in here to the vacuum. So the specimen was then consolidated the same way that we do for shear testing, and then, you know, he tested and started working on that. So we're talking about 1956, all right? So a little bit ago, not for us to be doing that in the lab. What he did, he found a nonlinear variation of the shear strength with respect to suction, right? He put this one, he put at different suction levels, and he said, obviously, with this kind of setup, you cannot go more than 90 kilopascals, right? You're going to start getting into cavitation, because, you know, you're imposing a negative pore water pressure in there, right? And I'm going to talk a little bit of axis translation in here in a minute, but basically, this one is imposing a negative pore water pressure, and therefore, he didn't go far. But he shows like there was an increase in the shear strength as your suction started increasing. That's the important part of it, right? He didn't attempt to derive any equation on that, but he shows a very nice increase, and there was a point when it started to settle down, like leveling out or going down a little bit. And as a matter of fact, if you continue that for a sand, that thing gonna go to 0, right? When you have higher suction value means 0 water, right, between the grains. And what's gonna happen, right? That sand castle is gonna go down, right? No water. So the shear strength will go all the way down again, right? It's gonna plunge. Then Bishop, again, he did a lot of work on testing, on triaxial tests, and he also modified that. And it's the same thing, you know, you modify that by putting a porous stone, instead of putting the porous stone, putting a air entry value, right? In such a way that when you applied your suction value, you only allow, okay, water to go out, not the air, right? And that's the way that you were able to measure that. So, but what I want to show in here is that Bishop said, okay, we can do CD test, consolidated drain it, CU test, right, consolidate and drain, UU test, we can do uncompressive test, unconfined compressive strength, but also we can do what he called a constant water test, okay? And I'm going to show you in a minute what is that. Then Escario comes in here, and what I want to show in here for Escario is that, okay, the axis translation technique, okay? So he said, well, I cannot go like Donald, that you put suction at the bottom of your sample, right? Because after 90, I cannot measure anything, all right? So what he said is, okay, to me it's easy probably to say, okay, if, I need this first. I'm learning, huh? See, so if you have pore air minus pore water pressure, and let's see, this is the suction value, right? And I'm going to put a suction value of equal to 150. Okay. So you can get that suction value by putting in here atmospheric pressure, open the sample to atmospheric pressure, minus putting a negative pore water pressure minus 150, right? You get cavitation, boom. It's difficult to do, but this is the concept, it's negative 150, right? Or you can do exactly the same by putting a pore air pressure in here of 50 minus, and how much pore water pressure you're going to put in there? How much? Minus 100, right? And that's going to give you the same 150, right? The same 150. So now you got 100 kilopascal. You are close to the point when you don't have cavitation. Or you can say, okay, I'm going to put in here a pore air pressure of 100 minus, and how much will be your pore water pressure? minus 50, right? And that's going to give you the same 150, right? Here we go. So now you can do this by translating both stress states to a scale that you can measure in the laboratory, all right? And that's basically what we call axis translation technique, all right? And that's what we use on the devices that, we got the odometer type devices, right? We impose a ported pressure of our suction value that we want. Okay, in this case will be 150. And then we keep our bottom, okay, saturated in contact with the water of the soil, and that is open to the atmospheric pressure. Therefore, the port water and the ported pressure are the same, okay? So port water pressure will be 0 right there, right? Because it has no pressure at all. So basically it's minus 0 here, and that's going to give you your 150. So for us, it's easy to just control the ported pressure, control this one, and that's the way that we put our axis translation technique. Everybody understand that? And okay, I'm very sure. So this is what I want. Escario start doing that. In 1980s, he started doing the axis translation techniques, which were actually very good. And in order for you to have that, obviously you put port air pressure in that, and then you just want water to get out there, right? If you get air out of that ported air entry disk, then you're going to dry your sample. You're not going to be able to get anything, all right? So he introduced that, the high entry disk that we were using. He applied any normal stress on the top, and he was able to do. And another nice thing is he started looking at, this is the net normal stress and the shear stress. And this one is for, let's say, the zero matrix suction, the saturated condition. And then he measured at 200 kilopascal. Now he was able to measure, now we're talking about 800 kilopascals, right? He was able to measure much higher suction values. And he found out that the shear strength will increase as your suction increase, and that the lines were pretty much parallel to each other. That's what he observed. A little bit different from this guy, right? Okay, so then Johan Fredland in the 1980s, what I want just to, again, this is a very nice history for you to read if you are interested on that, and I put all of that. But again, he found that for a planar failure envelope, the internal friction angle is assumed to remain constant under saturated conditions and unsaturated conditions. So no matter what condition you are in the soil sample, your phi prime kind of remains constant, right? Remain constant. So the contribution of the phi prime is independent of suction, right? Because it's a function of the frictional nature of your soil. So the effect of matrix suction is clearly shown in here. If you keep this one and matrix suction in here, will be the phi value will be this one, the first one, 33.4, and then you start increasing your suction, and you just measure what is the suction versus the shear stress, and you can see the contribution going up. And basically he imposed also an angle on that and said, okay, the contribution now can be measured independently from phi prime, right? And now he called it phi b, phi super b or whatever, right? So this one what I want to show in here, that's Fredland's model. And then he came out with this model, right? He said, okay, we do have the two stress state fundamental variables that I talked at the beginning, and you're going to have in here the C prime. Fine, we're just going to keep it in there for any reason that you got, right? You're going to have in here your net normal stress multiplied by your tangent phi prime. That's the contribution of your load. And this one is the suction contribution times tangent phi b. And this is perhaps the easier way that you can do the extra increase on shear strength due to the suction value, okay? So what factor is in there that difficult to find for you? Phi b, right? That's phi b. That's the guy, right? That's the guy, because the other one you know how to do it. C prime, phi prime, you know how to do it, right? You impose any stress state; those are independent of whatever you're doing, And the only thing you need is going to be the property on tangent phi b, right? What is that guy? All right, so this is the holy grail of this one. This is when everybody's been focusing later on. The good thing about this one is that that extends, or basically this one is the general case of the saturated case that you'll be learning always, right? Why? Because if you have a saturated soil, what is going to be your suction? 0, right? So this term goes to 0 if you have a saturated condition. And then you're going to have in here, and the pore air pressure is going to be equal to your pore water pressure. You know, if you have, the same pressure when you have saturated conditions, right? And therefore, the general case becomes the special case of saturated soil condition. And that's the important thing for this equation. So that's the shear strength. You're going to need, these are your soil properties, C prime, phi prime, and phi b. And basically, you can also do, which is, like everybody's doing, okay, what is cohesion? This one, that's what they call apparent cohesion, right? You're going to see your Holtz and Kovacs books, the very classic introduction to geotechnical, and they call it apparent cohesion, right? And now what he said, the true or total cohesion is going to be given by this value and this value together, right? So basically you can combine this value and this value, and that's, again, I'm giving you the secret to do your slope stability analysis. All right? Using a program that doesn't include unsaturated soil mechanics. All right? You go ahead, find these parameters, add it to your cohesion, and that's the point that you put in there. All right? That's how it is. So basically, you can do a total cohesion, which is a function of the shear parameters C and phi b and the applied matrix suction in there, right? So you can combine those two. All right, so that's what I wanted to show you out of this. This is how you can represent that one, right? And now you have two stress state variables, right? The one which is the net normal stress, and if you just check, the same concept that we did with the Mohr Coulomb envelope, you can do a total stress envelope in here. But if you do have here a third, a three-dimensional, and he put it always on that direction. I like to put it in this direction. But anyway, when you have suction equals 0, you are on your saturated case right there, right? Saturated case, right? So these first in front, more circles below are for a saturated element. And that's your envelope for a saturated element. All right? Now, if you increase your suction, your more circles are going to be, this one at the same confining pressure, it's going to be bigger. You're going to get, because of the contribution of your suction, right? And what is the contribution of your suction? Then you're going to have in here, on this axis, the C value that you got, which remains constant during the whole C or 0, plus the contribution of your suction in here, right? Order minus pore water pressure, tangent phi b, and then you're going to have higher. So as you increase your suction, the same more circles can be seen to be increasing, right, in size. And then if you just put everything on one plane, basically it's going to look like this, right? Right? It's going to be looking like that if you just put it in a 2D-dimensional plane. So that's, but basically the suction will create that extra plane that you can just draw like that for simplicity. Okay. Well, as the pore air pressure becomes equal to the pore water pressure, yeah, that's for the first one in here, and the failure envelope has a slope angles of phi and phi b with respect to the net normal and the matrix suction respectively. Okay. Many people measuring phi b. This is, like I said, it's important to understand now to know what it is, and they most of them have found that, yeah, when you have the phi value for different soil types compacted at the same water content that for the phi b, and then looking at the phi b values, all of them, the phi b is less than the phi prime. Okay, so the contribution is slower going up. There are numbers in there for some clays, silts, tills, and so forth. And it seems consistently working on that. So the shear strength, if you just check the shear strength versus suction plane in here, that you can see that the shear strength will increase with respect to suction, and it's going to be defined by the phi prime, phi b angle. Now this is debatable. I'm going to show you some data that it just give you otherwise, and actually the same Escario data that you saw from the 1950s or 60s shows that there is some nonlinear variation of that, okay? And again, you can use it as a total cohesion in an unsaturated soil if you want to use the theories that do not include the phi b value right there, okay? That's what I will show you, like the increase in the shear strength as you increase your suction value. Now how we measure either in the triaxial machine, like I showed you before on the history, or we measure it in the direct shear machine. Then the equipment needs to be modified. You need to change, for example, the area entry disc at the bottom, or put a colloidal membrane on that, or you have to encase your direct shear to sustain your potted pressure. For example, you need to do it in a chamber, right? So there are modifications that you can do for that. There are also triaxial apparatus that if you cannot modify them, you can do some stuff, right? Some stuff to figure out what is the suction. And you can test several samples of non-suction. So you just put your sample, for example, in a place when you can reach a suction value, and wherever the suction value is ready, you just translate it, right, to your triaxial machine and do the test, okay? That is good. I mean, the triaxial test, the samples are like this. So, you know, to do that one is have you done that, Professor Bharat? Have you equilibrated samples this big for suction before putting in a triaxial machine, or you have done them directly on the triaxial machine?
We didn't do suction control trial.
No, we haven't done that. Yeah, that's not an easy thing to do. Yeah. Totally not easy thing to do. But if you are using the small direct shear testing, you know, that's what I'm doing right now. Basically, I can put it on the cell, the Fredland cell, right? You apply the suction. Wherever you know that the suction is ready, get this one, get to the direct shear machine and shear it, right? Now you know what the suction value is. Okay, so you can do tricks for that, you know, to figure out what this one. Another one that we've done is like compact the soil at optimal moisture content, for example. Okay, and you let it dry or let it wet, let it dry or let it wet, and you have separately find out your saltwater characteristic curve, right? So basically, if you know what is the moisture content of your sample, you can imply your suction out of it, right? And then being able to share your sample and imply the suction from the saltwater characteristic curve. So there are ways of doing this thing without modifying this one if your laboratory doesn't have the capacity for that yet, right? The tests are usually longer for saturated conditions. Why? Because now you're going to have to consolidate your sample. And remember, the consolidation is a function of your unsaturated hydraulic conductivity, which is much lower, orders of magnitude lower than your saturated guy. And therefore, you're going to have a longer test durations. Tests are more demanding, and we're going to go for that in a minute, because now you have two phases, the water phase and the air phase, right? The water phase and the air phase. And now the water phase can be drained or undrained. And now the air phase can also be drained or undrained. All right, so you do have those two phases to control the drainage condition. And the triaxial set must be modified in order to measure and control the air, which is expensive. And that's why predicting models are usually desirable, right? Desirable. These are the tests that I check with Bishop. He said, okay, we can do the same test as we did for saturated soil. We can do consolidated drain test in which both the water and end phases, you need to understand that when you do unsaturated, you need to think on both phases, right? Think about the two phases. Water and end phases can be drained during the direct shear on this one, and the volume change during the shear can be measured. When you have a constant water test, this is the one that I usually do, okay? Basically, the air phase is drained, okay? You can do this one, drain, or control it that way, while the water phase is undrained. So you then get the water out of it, but the pore water pressure can be measured, right? The pore water pressure, because you have an undrained condition. When you have an undrained condition, you can measure, right? When you have a drained condition, you are controlling, right? You are controlling. Or you can have a consolidated undrained test with pore water pressure measurements in which the air and water phases are sheared in an undrained mode, and you measure the pore and air pore water pressures. And the consolidated and drain test, UU test, specimen is tested in similar way as the saturated specimens. They determine water content that you need to do. This is the total stress kind of analysis, right? And the unconfined compressive stress, that this has been used forever also. Total stress analysis when you're, confining pressure is 0 and then you just shear it. Obviously, the only soil that you can test is the one that can withstand with no confining, right? So no sands are allowed for that. So the direct shear test seems to be superior for testing unsaturated soil due to the reduced length of the drainage path, right? It's a little bit easier for that. Faster equalization. But even though this something like that can take 3 days per test, okay, and actually I don't consider this to be a long time. I've been taking more than that for sure. But there are the same problems associated with direct shear, right? There is stress rotation, there is only strength parameters are failure can be obtained. You can't just do much about that, but you can imply some data out of the direct shear testing that are important for us. This is what we're doing right now in this one on a direct shear testing machine, and I just, my student Kalani, she's from Sri Lanka, and she's doing a tremendous amount of work on trying to figure out the direct shear testing for different matrix suction conditions, and also for interface between geotextiles and the soil, so that I didn't bring the geotextile in here, but because of the topic, but basically she's using a couple of soils, get the grain size distribution, Atterberg limits, everything for that soil, and basically this is the kind of data she's obtaining right now. She said, please tell them do not publish this one because I haven't published, right? So this is unpublished data, but basically it's a different suction values. She put water content in here and she put the suction in here. This one, we're trying to go as dry as we can on those samples, right? As dry as we can. Because you can see on expansive soils, silty materials, that we don't have data that goes more than 100 kilopascal, 120, 200 kilopascal. Well, clays have more suction than that, all right? So that's what we're trying to do, is to figure out the whole range of suction values for that. So we're drying it very much. And this one is for the frost heave soil, which is a silty, is a CL value, I think. It's a CL's ML. The other one is a CH. And this is the data. You see, this is the saturated condition. This one is the optimum condition. And they're very close to each other, and they're parallel, like Fredland and many have reported on that. But when you start getting into lower water contents, that deviates from a linear relationship, okay? So the phi value starts pretty much, the phi B value we can imply from here, but only to the optimal moisture content. Now she's making more samples in here because I'm interested on that. And then you start looking at that kind of variation when you get into the dry condition. So we jump to the expansive soil, and it's the same thing, saturated condition, up the way to the optimal moisture content, you can get very good linear relationships, and more or less parallel to each other. So that's great. That's what is being reported. But again, when you start jumping into a much higher suction values, you're going to see a deviation from linearity on those things. So this we found this to be important. because there are a couple of researchers that have found that, right? And to see we can just tune up that equation that I just showed you before, right? The phi-b equation. This is the shear strength variation in terms of suction. If you put it in a arithmetic scale, you're going to see how it just, is a value here that is kind of jump up, and then it just slow down as you increase your suction value. Same thing here. So there is a point when there is no more contribution of soil suction appears to the shear strength of the soil, at least for this one. And again, there are some, if we go for a sand material, right, the third soil, I'm very sure that, very soon in here we start just looking at the going down strength right there. But this is also important. It's not the optimal moisture content. It seems to be a little bit less than that, right? So we need to figure out what is the relationship in there until what contribution and why we got this leveled out. This is the phi-b value that she's finding. Okay, that's the variation of the phi-b angle with soil suction. As you can see, it's a constant value, at the beginning, equal to the phi-sat, the phi prime. But then, as you start increasing your suction and you're passing the air entry value, seems to be like, you just go down with the contribution of time. So this is what we're looking at. That I think is interesting data to show, and it's a very good set. It takes a long time to get a good test well done. Okay, so based on that, she's proposing some model equation like the Fredland model that I just showed you. With the data we got an R square of about 73, and if she just put a power model for the suction value, right, instead of a phi-b value here only, she put up a power model in here. She started finding that the R square increases, okay, and she's looking at exponential functions in here, and that's what you do. You're modeling different scenarios to figure out. But definitely, we're trying to figure out if that model can be improved with a simple model as as something like this. And it seemed like we can improve some of the model. Obviously, this one is for a particular set of data points and soil types, right? We're going to need a bigger range. So hopefully if you guys have any data on sandy materials or something, we can all contribute it to, some data for the literature. All right. So this is how we measure, right? That's how we measure. This is how we work on this equation to figure out what there is the shear strength. And basically, if you don't have that, how are you going to estimate it, right? How are you going to estimate that? Well, there are some estimated values, and again, the first one that was shown and is being, very famous, and again, I gotta bring it in here because it's part of the history of unsaturated soil, is the Bishop equation. This is a predicted value. Why? Because he gave us values of chi for different soil types and different degrees of saturation, right? So that's our predicted values. So you got your chi value here, but again, this is that means that the contribution of suction and the contribution of normal stress are the same, right? For tangent phi prime. Anyway, but this one is one of that. There is another one. There are several equations that are empirical or based on the soil water characteristic curve and the saturated shear strength parameters, right? In all of them, phi prime is equal to phi b for matrix suction less than the air entry value. That's what we found also in the laboratory now. There is a point, this is the air entry value. There is a point that, it starts changing in here. Plastic clay seems to be going in this direction, like power. When you get silties, I found also a little bit bumping down, but, sandy soil definitely goes down after you just get the soil drier and drier. There are several equations that can be predicted, not only the Fredland. Vanapali did a great job, and I think, Professor Vanapali has been here also. He's an amazing researcher and has done a lot of work for unsaturated soils. Villar, okay, Khalili, okay. There are many, many researchers, and I gave you those equations. If you want to try different models for your data, it's an important that. these are, of interest to me are the Pali, because there are predicting using the saltwater characteristic curve. Those are the parameters for the saltwater characteristic curve. This is another kappa parameter in here, which he and Professor Freland gave values. Where is? Didn't bring them. Okay, here we go. Gave values based on plasticity index, right? Which I think I found them interesting, right? Because it's, those are estimated values. You can find, this is Marinho, this is the group from Brazil, which is actually great too. So they do have a lot of gray material in there, where if you have the plasticity index of your soil, you got your kappa value here, and then you apply this one to a volumetric water content in here, and then actually you had the rest of the parameters ready. So it's very interesting equation that you can use. Okay. This is Houston, 2017. She uses the equation by Freland, and basically what she did is she found a ratio for phi b. Okay, so we're going to jump into here, and basically she found kind of, to the air entry value, definitely this thing is a constant, and then she found a hyperbola going down, in which the phi value is a function of two parameters, A and B. This is your suction value. And she found the A and B based on, I didn't bring the B, should be here. Yeah, B is a function of phi prime, found it in here, and A is a function of grain size distribution. So this one is, I'll give you a summary of the method that Professor Houston also put together for that. But basically, you go to the laboratory, you determine your C prime and phi prime, right? Your saturated parameters. Then you estimate the hyperbola fitting values, A and B, from gradation data or whatever you need for that, and basically found the phi b for that, and just apply the equation, and then you got it, right? At least you have an equation that is much better than using a saturated soil equation in a problem that you needs to improve. Okay. Applications, there are many. Again, I just brought you some soil stability analysis in here. But basically, this one is what we do on this, all right? There are some methods that have been start including those into the program, but I haven't seen like C-pitch analysis. You can do an unsaturated C-pitch analysis these days with Plaxis, CW, all other programs that everybody are putting together. For this, I haven't seen many of variations that include phi b. There are some stuff in there. But basically, the method include, for example, to solve the entire wedges, the free body diagram, or method that divide into the method of the slices, or optimization techniques that you got in here. So, for example, I just want to show you how you can modify a normal slope stability analysis, right? In which you do have a wedge and a full free body diagram, in which you have here, for example, the slide, right? You have your external forces, lateral and normal forces. You got your W here, and you got your shear force and your normal force, right? This is how we do that one. And then you're gonna, and this is beta is just the size of that slice. Alpha is the slope at the middle of every one of those slices, right? So this one is a normal configuration for you to do a slope stability analysis, right? So once you have this one, and basically what you need to find out is your shear force in here, right? That's your shear force. Okay, so what we do with the shear force is, as you solve your free body diagram, you're going to find that the shear force is the length of the slide, and you divide it for the factor of safety. That's the one that you use for putting in here, and then you put, the stress, right? The stress multiplied by the area will give you the force, right? And here is your stress, and you can just put the Freland and Sin equation right there, or any equation that you want or need, right? So the mobilized and the base are going to be just a function now of the normal stress, the port wire pressure, the net normal stress, the cohesion, anything you have, and the pore water pressure right there, right? All of these act to this point, and then this is the equation that you can use. Now, consider that the matrix suction as part of the cohesion. And I think this is the best way that you can go, right? You go ahead and say, okay, this equation, the whole equation that you have in here, I can combine C prime plus the contribution of the suction into a total suction value, total cohesion value, and then in here you do have the shear force. So you can use the C value, that force in here, and the shear forces, the two forces that any computed program will allow you to enter, all right? So that, you can contribute it for some of the areas, the different unsaturated soil conditions that you're going to have. So this is what I believe is that's what I've been doing, and the results are okay until we found programs that include tangent phi or other models available in here. All right? So do you guys have any question for that? Yes.
Yes, ma'am. I have a few questions. The first one is about that phi value that you have presented. You have shown some results from your PhD student. Can you please go to that slide?
Sure.
Phi variation with suction. Yes. So it seems phi decreases with suction, increasing the suction. So yeah.
Correct.
Does it mean to say that the contribution of matrix section will be maximum at fully saturated state, or
Correct.
Before the area entry value?
Not the fully saturated state, but there is contribution, is increased. The contribution will increase linearly, right? Linearly, the phi will be the same, right? The phi will be the same. So if you plot shear strength versus normal stress, versus suction. We don't have that one? Shear strength versus suction, right? Okay.
I think if the phi the initial shear strength is increasing with matrix suction, phi is constant, which is equal to phi dash.
Yeah.
Later on, phi is decreasing, it will go to negative also. So that's the actual exactly problem. Initially, Bishop's equation was criticized, saying that the chi value is not constant. Chi is also dependent on suction or water content. Initially, Fredland thought it's phi is constant. With 3 data points, he thought it's going linearly, and he proposed that expression. Later, it is realized that phi is also dependent on either water content or suction. That's why it boils down to the Bishops. So reason is, if you go back, this results if you see, the nonlinear effect that is coming towards the higher suction is because.
No. Okay.
I'll just finish my this sentence. Initially, when the higher moisture content if you have in the soil samples, you are trying to fit using effective stress principle or whatever, C dash, phi dash, all those things. At very low moisture content, do you think you can use C dash and phi dash to fit that? When soil is nearly dry conditions, it behaves like undrained. Water doesn't come out. Same soil, when the suction is changing or when the water content is changing from saturated to dry state, the behavior changes. If you try to shear the sample when the soil is nearly saturated conditions, drainage takes place. Water can come out. But nearly dry state, water cannot come out. It behaves like an undrained manner. Right? There is a phase transformation that takes place from air to water or water to air. Either vapors are formed or air is actually getting into water as solute. That is what is happening at higher suctions. So therefore, fitting everything with one single equation, which is based on C dash and phi dash, is the problem.
That's correct.
Yeah.
Now, what happens when you test a saturated sample in an undrained condition?
Yeah.
So you are not moving water in and out.
If you have a saturated sample, if you are doing an undrained test, we never use C dash and phi dash. We only measure undrained shear strengths. We measure if your pore water pressure is estimated, then we have effective stress you have to bring. But Fredland one, you cannot segregate effective stress concept. You can only use sigma dash there instead of sigma, and then you have to bring there.
You can, well, yes, I think this is a great point, but I think for any suction value, you can always measure what the pore water pressure or the suction contribution is given, right? And that's why we don't put them all together, right? We put them in 3 dimensions, right? So you're right, when you have a saturated condition, then you have your total stress analysis in here, or the total stress analysis in here, and then you got a pore water pressure in here, and this is your effective circle, and this is your total circle, right? This is your pore water pressure. Okay, basically, if you do that, if you measure the pore water pressure, you can get CM phi. You can measure phi. And I know that you said on the one of your first lectures that you know, that it's either UU or CD, right? So you can.
CU or CD, not, I don't use UU by the way.
Oh, you know.
I don't use UU.
So yeah, it's CU. So you can get the contribution of your suction or your pore water pressure when you have saturated soils easily, right? When you start getting into the dried samples, you're right. You know, this more circle is going to be increasing in here, and whatever contribution is in here was because of the suction, right? Because of the suction value.
See, measuring suction at shear plane during failure is like kind of impossible.
Yeah.
The reason is you are trying to measure. Most of the tensiometers don't work beyond 100 kilopascal because of vaporization. Because the pore, vapor pressures are, the total pressure reaches to vapor pressure, so cavitation takes place. Same thing happens, the air is not full air. You just to say that UM is suitable, I'm trying to measure. Now some of the things are available in the vapor, water phase, and air is available in solute. So measurement is a big problem. Although we are saying that I'm controlling suction, you are controlling suction at these two ends.
Well, it's the
Right,
same.
so-
It's the same thing that we had for any soil, in which we figured out that the volume change is occurring or not occurring. When you do have undrained conditions, it doesn't mean that the moisture is not moving from this point to this point, or from this point in the shearing failure to another point. What you do is to do an overall estimation of that the sample, you're not going to get it out, right? But it doesn't mean that the water will be moving, unless you're going to tell me that the student did a wrong.
No, I'm not judging.
A wrong equation, a wrong test.
I'm not judging your students' capabilities or anything.
No,
I'm just trying to tell that, in saturated state, when you are doing undrained test, I'm sure the water is moving. Imagine water is available as a lens around the particles at a very high suction value or very low degree of saturation. Do you think water moves that freely? Where if you estimate the hydraulic conductivity is nearly 10 power minus 14 minus 15.
It doesn't move.
So that's the condition, right?
That doesn't move.
Yeah, yeah.
But what I'm saying is, for the saturated condition, if you have a saturated condition, if we consider that sample to be undrained, on the shearing zone it's not undrained.
That's what I'm saying. Near to saturation, even Bishop's equation works very well. Correct? Yeah. So all of them work because.
Well, but just for saturated conditions.
Yeah.
85 or plus, that's
Yeah.
what we said. Those are all great points. But it's absolutely right. So that phi B varies. There are many reasons why phi B varies or not. But, Professor, but it's true that, probably there is not only those two, that we have to measure that, right? There's going to be more stuff that we need to add in there as we get the soil, the menisci much smaller and smaller. Other forces are acting in there that are just different, okay, that are contributing to your shear strength, right? But this is what that, if we are trying to beat the most famous equation that is in there, we're going to need to start by trying to figure out what they're doing, all right? So anyway, great conversation in there. Any other questions?
Sorry, invited Danish's question. I don't know
Yeah.
what he wanted to ask.
Well, Danish's question was, but still a contribution. There is a contribution up to that certain point.
Right.
And then when just flattening out, there is no contribution, right? There is no contribution of the shear strength to, there is no contribution of the matrix option to shear strength pretty much.
Okay.
Okay.
And if you could go back to that earlier slide,
To
the
the
previous one.
Previous slide. Previous slide.
Before this one.
Oh, right here.
Yeah. Here, the normal stress that is shown here up to 80 kPa. I was wondering what can we expect if we go beyond 80 kPa, higher normal stress.
Higher normal stresses. Material crushing probably. Okay, so you're going to have
Okay.
much more, well, if you are just figure out what the shear stress, the normal stress contributes to the shear stress is, right? How much load are you going to be putting there, and you're going to start increasing there. I guess what people that have done that have find out that you start, not for those oil, but for more granular material, you start getting into the crushing, right? Into the crush, and the more envelope start going kind of down.
Okay.
Kind of down, right? It's not a linear anymore, or flattens down.
Okay. And
Do you have any?
And behaves like a brittle material,
What again?
not a ductile material. Behaves like a brittle material at higher normal stress.
Yeah. Okay. So exactly, you can get some straightening in there too.
okay. And you mentioned that the right-hand side figure is for expansive soil. That one.
This one is for expansive soil.
Okay. What was the PI value or plasticity index in that one?
It was rather kind of middle. PI of 32.
32. Okay. But these are all direct shear tests, right? So-
Direct shear test.
Okay.
But they're being consolidated separately to the normal stress that you put in there. Okay, that's why those things shows they should be kind of flattened down, right?
Right.
Right. But they were consolidated first, and then you just move to the direct shear machine.
Okay. Yeah.
Alrighty.
Adding to that question,
Yes.
the next slide, can you please go?
Here we go.
The next one. So, how did you measure the suction, the measurement device, like for lower suction values?
Low suction
so-
values. These ones. Okay.
Yeah.
How we measure low
Yeah.
suction values? Okay. So what we do is we just get the sample, we put it on the pressure cell, and we just equilibrate it to the suction that we want, or to the pretty much the water content that we want. So we know how we estimate. We compacted the sample always at the optimum moisture content. Okay, and then after that, basically, we just put it on that, and we start, letting it dry, by applying a particular suction, right? When we know how much water is going out, and we know that the water content is what we want, we know the suction value, because you got the saltwater characteristic curve, right? So pretty much what you do have is the saltwater characteristic curve data. Water content. Did I do? It's this one, right? Water content versus suction, right? So what we got in here is I want this to be at this particular water content, say gravimetric, okay? So that's the guy. So this is your suction for that point. And you get that suction value, and then we just put it for the Phoebe value. So we didn't make, we haven't we did not modify the shear strength cell. We did not. Okay, we just shear the sample at a particular suction value, and a rather high shear rate. That's another thing. It's a high shear rate, so we avoid any drainage condition that we have, right? Any drain, and that's all that it doesn't drain in like in 20 minutes. That is last at all. So that's how you do it. So we put it on the saltwater characteristic curve. We figured out the suction of the water content that you want to test. Once the sample is at that condition at that point, you put it on the shear strength device and you shear it. So you shift it like that. Okay. All right. Any other questions? We got a break going on? Ooh. 10:30? No, what time we start? 10 to 11?
Break is at 12:30.
12:30, right?
Oh, 11:30.
So we are on a break, right, by now. I'm sorry, guys, but it was his fault, not mine. Yeah. All righty, so I'll see you in a bit to continue that, with the. Okay, here we go. need to turn this on first. Okay, it's on. Now it's on. Okay, thank you. How can I? Where are the lectures? Local disk. I was here on John 18 0. One up. No, go back. The second one on the list, I think it is. Yeah, this one. Day 4. Second day. Thank you. Alrighty, are you guys ready? Alrighty, so we're going to talk a little bit about volume change, stress deformation for unsaturated soils, and again I'll continue with my theories of dividing the stress state variables into two different, combinations, right? Great discussion during the break on how you just, if you combine the normal stress with the pore water pressure, you're working still with an effective stress, and but at the end of the day, we obtain the same results actually if we use those surface and those two kind of three-dimensional plots. And we're going to see that on the volume change right now. So what I have here are constitutive models for the stress deformation of unsaturated soils. Again, I wanna start from, again, this is the models that we have been using, but that doesn't mean that there are different models available as well that are working. And the compressibility of unsaturated soil. So how do you translate this one into the geotechnical engineering practical? So again, this one I wish we can bring it up on the first thing here. There are many different stress strain models for unsaturated soils, okay? And all of them constitutive in nation, but some of them are just, giving different assumptions. One of them was for soil is pure elastic. Some of them are pure elastoplastic models. And then you just, go into the elastic model. You can use linear models, non-linear models, or, all of that. And in the elastoplastic models, you can also do a different set of models in here. And basically, this one is nothing but what is a model, like, is something how you're going to be estimating or representing the stress strain behavior, right? So you can do a model that, is just, creeps away like that, or just start hardening models, or you just, a relaxation, or you just kind of unload it. So it's not how you represent that. And it has to be whether you include only elastic side of it, or you include the elastic plastic behavior of the soil, right? Some of them are going to require loading and unloading. So how much of this strain is reversible, how much of this strain is not reversible, and so forth. So there are many models available for doing that. But again, Fredland and the colleagues, which is the theories that I manage, they basically use a non-linear elastic, kind of incremental elastic model, right? It's an incremental elastic model. Suction with hardening plastic constitutive models for unsaturated soils. But we're right. If we keep going with the matrix suction, we start increasing the matrix suction, the soil will lose all the strain parameters because you have no more water, right? So all of them eventually will just go to a point that it's just going to go like that, and obviously hardening behavior will not be anymore. But for the range of suction that we're working in our soils, probably unless we are in the moon or in the, I don't know what desert, then we're not going to have that falling down, right? So elastic models are modified incrementally, that's what they do, and the modulos are based on the voice ratio, state surfaces. basically at first defined by Matthias and Radhakrishna in the 1960s. We got Poisson's ratio is typically estimated. You can, certainly measure that if you have the means of doing that. And in general, there are path dependencies not incorporated into those models. Okay. The more Coulomb failure, surface expands, exhibits hardening with increasing the soil suction, via an increase in apparent cohesion, like I just showed you before. We can include that matrix suction into that. And also exhibit softening with decreased suction. So volume change can be expressed in terms of deformations of phases of the soil. And again, we can use different phases. The two sets of deformation stress variables that are required are the deformation of the state variables associated with the soil structure, and those deformation of the state variables associated with the water phase, the two of them. So if you consider an element of soil that deforms and it applies different stresses, you consider like we did it before, the contractile skin as part of the solids. You can say that the change volume with respect to the initial volume is going to be the change in volume of water plus the change in volume of air if you consider the solids to be incompressible. Okay? So the overall volume mass constitutive model, and we're using again linear elastic incremental model, right? So segments on that and just to get the nonlinear behavior, but it's just basically multi-segment. We need a deformation state variables with the appropriate stress state. Remember that you're going to need the stress and the deformation, right? And these are the questions that we do have for linear elastic in the 3 dimensions, in which you include the modulus in here, stress, the modulus, the stress over strain, and include to get into the 2-dimensional or 2-dimensional, you're going to need the Poisson's ratio right there, all right? And the total volume strain is going to be the summation, again, superposition of the strains at the 3 directions. So when you have a saturated and an isotropic, okay, linear elastic soil structure, the stress-strain constitutive relationships are pretty much the Hooke's law, right? That part of it. And the volumetric strain is the sum again of the normal strains right there. So the volume mass constitutive models, when we talk about normal strains, the normal strains in here for unsaturated, so these ones were, for saturated isotropic conditions, right? For saturated isotropic conditions. When you get into the unsaturated isotropic conditions, basically you're going to need to add the extra component, okay? Again, I divided the normal stress in here, the water, I put it with the total stress, so I don't use effective stress, and I put on this side the matrix suction, right? The matrix suction contribution to that, which is going to have their own modulus. In this case, going to be the modulus of elasticity for the solid structure with respect to change in matrix suction, okay? So all the volumetric strain is going to be the sum of the normal strains, the same way as we did before, or we have done before for saturated soils. We're going to be doing it here again for unsaturated soils. But now we're going to have the extra contribution of the strain due to the change in suction, separated from the change in the normal stress. Okay? So when you solve that, the shear deformations are going to be the same, the ones in the phases of the element that we consider. Going to be shear strains, and we're going to have normal strains in here. That's going to be, this one is going to be your 3-dimensional tensors for, or the shear strains, the normal shear strain that is going to be the deformation tensor. Okay? So the volumetric strain change is what we want, the change, when the change in the stresses will happen, right? So you're going to need is the volumetric strain change is equal to the volume of the voice change that you're going to have divided by the initial volume, all right? Again, it's a summation, it's superposition of the 3 dimensions plot. This one is the equation that you just saw before. for one condition, and then you solve for the change in the volume of voids when when you use that equation. So again, we got divided the two stresses in here. So that's the same equation. The constitutive equation for the water phase is going to be, now you're going to have the same equation, but now it's going to have for the water phase, right? And in here it's going to be the modulus for the water volumetric modulus that is associated with the change in the mean net normal stress, and this one is the water volumetric modulus associated with the change in suction, right? For the air phase, usually it is computed as the difference between the overall structure strains minus the water volume changes, okay? So, and now you do have the whole change in the voids by the change in the volume of water plus the change in the volume of air. So that's how we get those two parts. One with this equation, the other one, the difference between the one that you saw before and this one, right? So in that case, again, we divided and we used a three-dimensional plot analysis to figure out the constitutive surface, right? The slopes are given by the equation that you saw before, the changing strains. So if you check in here, the soil structure is going to be the volumetric strain as a function of suction, and the volumetric strain as a function of net normal stress, right? You're going to have the two stress state variables in here, and for the water, you're going to have the change in volume of water with respect to the initial volume of water as a function of suction and as a function of net normal stress. And you actually, what you have is a surface, right? As a surface, if you consider them in that way. If you do an arithmetic scale, it's going to look like that. And basically, for that, you're going to have a different, relationships that instead of, being that way you're going to have them on this nomenclature, but it's the same thing. It's just only on the arithmetic scale. One of them for the soil structure, and the other one is for the water content constitutive surface in the arithmetic scale. All right. So those are this is how we estimate the volumetric, the changes, the change in volume, and it's just a linear elastic theory, right? And again, this is just one of the models. Doesn't mean that there are no more models. There are many, many more models that are available, as I showed at the beginning, and all of them have a different way to estimate. So how we apply this one to our geotechnical engineering problem, right? For saturated salts, you are very familiar with that equation. This is your consolidation equation, right? In the arithmetic form with the change in void ratio as a function of the change in effective stress, because in the saturated state is you got the compressibility right there, right? The C sub C if you use the log scale. But this is the consolidation equation that you should all know about it, right? And be familiar with that. When you have unsaturated salts, again, you divide the two into the normal stress and the suction value here. And now you're going to have two compressibilities, right? The one is the coefficient of compressibility with respect to the change in their normal stress, A sub T, and the other one is sub AM, which is going to be the coefficient of compressibility with respect to the change in matrix suction. So that was the plot that Professor Bharat was doing here. That was the change in void ratio versus the stress state variables. They're going to be looking like that. They're going to be looking like that, okay? One goes independent of the other one, right? Independent of the other one. Same thing for the water volume change. You're going to have the coefficients of volumetric water change. Okay, let's going to go for the next one. And this one is for the water content. Again, for the saturated soil, you're going to have the change in water content with respect to the net normal stress, right? And you're going to have here a function on coefficient of water content change, right? With respect to the net normal. For unsaturated, you're going to have two. You're going to have this one with respect to the net normal stress, but this one with respect to suction, right? the B sub T and B sub N. The two of them are coefficient, and they're going to be behaving like that, separate to each other. When you look at the surface, it's going to be looking like that. Right? So those are the constitutive surface for the unsaturated soils. We're using just the expressions that we use, right? We just don't using the one that we use for constitutive model. But those are the terms that you become now more familiar with. Now, if we get into the compression index, when we get into the compression index, we use the log scales in here. Now remember so which one is the one that you'll be very familiar with is the change in void ratio versus the change in stress, right? The change in stress. And this one is a total stress change, which is you're going to have a constant in here equal to C sub T. The 0.43 is the change between log and arithmetic. In here, there is another one in here, which is C sub N, which is the change in void ratio with respect to suction. Okay? The other one in here is going to be the change in water content. Okay, now for this constitutive, this one, okay, when the soil is saturated, the potted pressure is equal to your forward pressure, right? So this one is like your suction, your effective stress, right? That's your effective stress. That's the consolidation curve that you've seen always, right? So what you got in here is this guy, right? Is that guy. And that's your, becomes when the suction is zero, just when the suction is zero, this one becomes your C sub C, right? Now, if you get into the water contents, this is the water contents, and this is the water content change with respect to suction. And you got this slope in here, and this is the water change with respect to net normal stress, all right? The surface will go, they don't go parallel to each other, this one might be much lower than the other one. But do you recognize this relationship? What is this relationship? The change in suction with respect to water content. That's your salt water characteristic curve, right? That's your salt water. So the extreme on that one, okay? If you just do a salt water characteristic curve with no external load applied to it, that's your salt water characteristic curve. Okay? So this is the corner that you have learned these 4 days, and this is the corner you have learned during your consolidation analysis, right? So in that way, you do have all the compressibility due to a combination of the effective the stresses in that way, and you can represent that one in a constitutive surface. There are limitations and complications, like we were discussing during the break in here, obviously. The loading part is different than the unloading part. So we're going to need a constitutive surface for the loading, right? And another one because we got a different unloading value. Instead of being the C sub S, it's going to be the C sub S, right? And also because we do have hysteresis in the salt water characteristic curve. And that fact means that, we're going to have a slope or a relationship for a drain curve and another one for the wetting curve, right? But knowing that, it's like going back and forth for wherever we need to go, right? It gets more complicated. But the theory applies whether you're loading or unloading, or the theory applies whether you're drying or you are wetting in here, as long as you use the right coefficient, right? The right coefficient in there. So, question for you, and I already gave you the answer. If you put this one into a log scale, right, you're going to look like this. So can you identify the consolidation curve for saturated conditions in here? Is this one, which I call 1, or this one, which I call 2, or with respect to water content, which I call 3, and this one, which I call 4. Which one are the consolidation curve for saturated conditions? That's going to be 1, right? That's going to be 1. And that's the one that you... And what's going to be the salt water characteristic curve for zero net normal stress? That's going to be 4, right? Okay. So this is important that you understand how we expand the same theory that we've been using before. Okay. Any question with that? Now I'm catching up with the timing, right? Yes, Himanshu?
Actually, we are having like water is incompressible, and we use it in the conventional compressibility theory. When we are having two phases, water and air, so air is compressible. How do we incorporate that?
The volume change due to the compressibility of the
Air,
The
yeah.
compressibility of the air. Well, again, it is included because the change in volume that you're going to have in here, the volumetric change in volume, is going to be a function of the change in volume of the water, okay? Which you're right, this is the water is much more incompressible, right? And this one is the change in the voids of the air. So they're going to be in here. We don't have a constitutive relationship applied directly to that, but if you come back to the volumetric change for the total, soil, right? The total. And you subtract from this one the one for the water, which is this one. Then you get the compressibility of the air. Once you get the compressibility of the air, then when you apply that, then you use that one in here plus this one in order to figure out the change in the water, right? So that's how that works. Any other questions on that?
Ma'am, can you explain this EW and HW, that water volumetric modulus associated?
So when you talk about linear elastic analysis, right? Linear elasticity or Hooke's law, right? So you talk about a modulus being equal to what? To the stress divided by the strain, right? So we're solving in here for the strain, right? Which is going to be equal to your stress, whatever it is, divided by the modulus, right? So if we're using the whole mass when it includes the air, the water, right? The whole mass of the voids that are going to be, changing in volume, we're going to be using the elastic modulus. We always use the elastic modulus for that, right? But when we use only for the liquid phase, the modulo of the water associated, all right, with this stress is associated with the normal stress. We call them EW, which is the modulus of the water, right? Depending on that one. So the modulus is not going to be your elastic modulus. Now it's going to be a modulus of the water modulus that is associated with that change. And in here, the Henry's guy, which is the water volumetric modulus associated with the change in the suction. It's another modulus. You see what it is? So there are 4 different modules that you're going to need probably. There's 4 different material properties that you need. Okay? And those are available. Okay? What do you expect for that? But actually this one is the one that you just measured. If you just charge some water, right? That's very incompressible, right? So the modulus is very high. That's what Himanshu's, okay? When you get air, it's going to be much lower, right? It's going to be very different. And when you have the change in water content, also you're going to have another module.
Yeah, ma'am, adding to that question only, regarding that HW, that is the water volumetric modulus, how to determine it? Is it experimental determined or?
The Henry's law.
Henry's law.
It is, there is data available for that. There is data available, but you can actually determine if you want it experimentally, but it's data available for that when you just, people have done the water and, have been associated with different suction changes or net normal stress changes. But this is Henry's law. So the values are available. You can see the values all over the place on tables. So that's what I think we'll use on that. I can bring that over. I could find those, but yeah.
Excuse me.
Yes, sir.
Just I want to ask that does this model capture collapsible as well as expansive soil?
No, that's what we're talking about in here. Well, you're going to see a model that I'm going to bring in here tomorrow for expansive soils that will do that, will capture that, right? But it's also divides the two stress state variables in here. Okay, so let's check this surface, right? The thing is, this one is only for linear elastic theories, right? This is for linear elastic theories. So what happens is, if you do have, let's say you got a soil that you're going to be decreasing your suction, right? Okay, so you are in a place in here, right here, okay? And basically, or just zero volumetrics, and then you're going to be decreasing your suction, which is putting water into the soil, right? So if the expansive soil behave the same as your, these kind of soils, they're compressible soils, then they will follow this line as well, right? And they will just go and compressibility go like that, and you're going to see what is the change in volume due to the expansivity of that thing. All right. Now, collapsibility. Okay, so what happens if at this point you decided you put water in there, and then you decided to load it? Okay, so that's what I'm arguing with your professor, that I think this works with no problem, because you just go ahead and just get the point. The problem is you need to really be careful with this guy, right? Because for expansive soils, the value is different. Now, when you get in here and then you decided to load the soil, okay, and now you're putting soil in this one. Now you are in one of these surfaces, and now you decided, and the soil can start going down, down, and there is even a point when you can get collapsibility due to that, okay? So if you follow the same surface, and I think this one is not the one that I like to follow, I like this small one in here better, but it's the same thing in here, right? Changing matrix suction, you just, this whole structure in here. So if you have no volume change, you increase your suction value. So you can go from this point, to this point. You got this value here, and then in this one you decided to increase, and then you just follow this guy in here until even lower in here. Okay, you ended up in a point on this. So now, whether the linear elastic models, okay, that we use, very simple. You see, the question is just a linear elastic model. You can use just, you're using, or we are using, only one modulus, right? Where is it? What is in just one model? Right. What? Okay. What is in just one values for those? That's what I'm saying. Okay. Because we consider this to be elastic in a certain range of values, and then we use another elastic for another set of values. Now you can do it as non-linear as you want, right? Depending on the values that you got. But you need to be careful with what we're using here. It's using with linear elasticity. Okay. But yeah, certainly out of a surface like that, you can do any combination of loads conditions, and you can have collapse in an expansive surface. Okay. Good questions in here. Any other questions? All right. So how is our schedule going on in here? So we have another hour, right? After lunch.
Around 22 minutes.
What again?
22 minutes.
We got 22 minutes, and then we'll come back for the last hour, right? So what I'm going to do, so we can go a little bit slower in the next topic, okay? I'm going to start right now. Is that okay? So if we finish before, but I'm very sure we're going to get the hour in here, right? So we're going to continue here for another 20 minutes. We'll finish, but we're going to go for the next, the application for that. All right, so how we do that? There we go. There we go. Thank you. Yeah, I tried always to reduce everything as much as I can because of the time, right? So this one was short. All right. So, and again, I'm going to jump in here into the practical side of our profession, right? And basically, as you saw yesterday, the way that volume change is predicted for or included into the pavement design analysis. It's a very empirical way of doing that, right? You get PI passing 200, infiltration or rainfall or something, and then you put them in this one, you add some roughness to the road due to that, and then the roughness will add, will just, you design for that roughness cap value, and that's how you do it. Well, we decided that, we don't want to be, if they don't want to run, by their pavement engineering, right? Pavement engineering designers don't want to run final element analysis and use the constitutive surface in here when we can go up and down, back and forth on time and space, then we could run some closed form solution for them, but based on mechanistic principles, based on the two stress state variables, right? The net normal stress and the suction values. And mostly on the suction values, because this is actually will change. When you have a road, if you have a road, the road has some overburden pressure on top, right? Has the granular material, the asphalt layers, and that thing doesn't change much during the year of the pavement. Right? Add a little bit of, surface layer or something, but actually the net normal stress, the static load applied to a pavement structure, is usually kept constant, right? It's kept constant, correct? So any changes in volume change due to the expansive soils, right? The expansive soils will be due to the changes in suction, the stress of the suction, okay? Now, if you go down with overburden, and that's, we're gonna see that, and I'm just putting everything in a little summary at the beginning. If you go down in an overburden, the overburden is going to be more and more and more as you go down, right? And that overburden is like adding load to your soil elements. Therefore, the elements of soil at a greater depth can collapse, right? Can collapse with no problem because you have a big load on top of it, all right? So this is the principle we're going to be using to estimate a much better value for pavement analysis and design based on suction, right? So how we predict volume change for expansive soils under covered areas, and we did that one for pavements. Again, I brought my nice pictures of cracks that appear because of the changes in the expansive soils. So, but and you're very familiar with the problems we face with the changes in volume due to expansive soils and the damage in roads. Okay, so we need the ability to continuous monitor volume, or to estimate a continuous volume change is important, and well, because we do have this one as a way of weather conditions. And again, I always, we're doing this graph for many times, but again, pavement design and analysis is the changes in distresses like fatigue cracking, PI. Fatigue cracking, and to close. Thermal cracking, IRI, rotting, and so forth. And it's the change in time until it fails, right? Until it fails. So if we are able to do that, instead of putting the IRI one fixed value that is going to be increasing the IRI, this is the IRI change, let's say due to the, to rotting, plus cracking, thermal cracking, plus fatigue cracking, and then if you add a little bit due to the expansive soil, it's going to be a constant, right? Because it's PI passing 200, and the rainfall, probably the rainfall is going to add a little bit more, probably on a jumping in here, right? In this case, we want to figure out how to estimate that volume change with time. So we do a better predictor in that particular parameter that we are using on the IRI for pavement analysis. So something that allows for the prediction of the potential cumulative pavement roughness due to the volume change was desired, and we got two great students working on this project about 3-4 years ago, Austin Olays and Mohamed Mosawi. Here. So basically, the general approach that we did was incorporating a suction-based framework for estimating the volume change of a shrink and swell, goes back and forth, due to the time varying effects, right? Time varying effects. So what happened with the climate and how this affects and how I can do that? How can I establish that? So we used to establish a deterministic approach for long-term volume change prediction. What is a deterministic approach? Well, deterministic approach is when you get a value, just one value, right? And you have no associated variability with that particular value, okay? That was, and again, we can do that one for probably forensic engineering, not for prediction, all right? So we did it for forensic engineering. Forensic is when you have to go to the field and figure out what's going on, why is damage, okay? Is that a cause of expansive soil? Now we need to figure out, right, how much that will expand. Litton, Bob Litton from Texas A&M, Albany, Bluth, a great group also of researchers that have done this. So we use the same kind of a framework that they use for post-tension slabs. Post-tension slabs are the ones that we use very common when we have expansive soils for residential construction foundations, okay? And basically, these are, way more ahead of design on expansive soil than the pavement people, okay? But we updated that, and we considered all the shortcomings that we got on this prediction, and we said, okay, we're gonna do a little better job on trying to figure out this deterministic approach that they have, okay? So we updated with consideration of short-term conditions. When you have a deterministic approach is when somebody asks you, okay, in the field, I do have this expansive soil, and I want you to take this laboratory testing and give me a value for the expansivity of the soil. You just give them a value, right? And usually you gave them a maximum value. That's it. Well, does that mean that's the one that we should be using for design? Perhaps not, if you have this changes with time problem in here. Okay. So we also updated, including an stochastic perturbation on that, because we said, okay, and every problem should be adding a stochastic analysis to it. Why? Because we're dealing with soil properties that vary absolutely tremendously from one place to another one. We're dealing with climatic conditions that if you use 1 year, the next year is going to be changing dramatically as well the next year. So you can have some patterns, but you have some variability associated not only with the soil properties, but also with the climatic conditions. And not only that, we also have a spatial variability. Okay? It's not the same volume change that you're going to get at the side of the road by the shoulder than in the middle of the road, okay? It's not the same. So there are going to be some variability associated in there that we need to take into account. So, and the other commission thing that we had to do was that should be implementable by practical engineers. In other words, they didn't want a final element analysis model, all right? They didn't want, I know we geotechnical engineers do it, we have no problem. Pavement engineers have trouble running something more than 5 minutes, okay? So they have problems. So he said, okay, we do have a guide. We got the IRI in there. We don't want to deviate much about what we're doing business in here, but we want a factor in there for the psi factor to be a much better or based on mechanistic analysis, okay? So that's why we went through this route instead of doing, modeling. So we implement a mechanistic stochastic approach to do that. What do I mean by mechanistic stochastic? Well, mechanistic means, it's based on proper theory, right? Proper theory and stress state variables. And the second one is stochastic. So I'm going to give them variability associated with that. That at the end of the day is the one that is going to give me the rawness of the pavement because of that variability. So this is the framework. We're not going to be working on that, but I'm going to be working on batches, right? Those. So, but I gave you the whole kind of a step-by-step procedure that we did, and all of these, steps obviously have a lot of work involved on that that I even didn't bring in here all that. But we got 16, 17 steps in there for you to read. But then I'm going to go through that into batches, right? So what did we do? The first thing was, okay, we need climatic boundary conditions, right? You're going to be doing that, so we're going to need climatic boundary conditions, and we use the same Thorwell moisture index that you did. Now you're very familiar with that guy, and we said, okay, we can modify this one from being an annual index or one number for that modified into a more seasonal variation, right? So we start working into monthly categories for that. So collected the data from a satellite data like MERA, for example, or NOAA. NOAA also has a lot of data there. I don't know if the climatic data is available for free in India. Is it great? Many countries you have to pay a lot for 1 year of information, unfortunately. Okay, so you got that advantage that you can get years and years of good data. And we collected that data. We extracted data from the nearest weather station that we needed for a particular project or road, right? And we included year, months, monthly precipitation, and average temperature. And why we went for monthly and not for daily or hourly? Well, because expansive soil takes time, right, to respond to that. So it will be very naive to think that you can predict everything that's going on every single day, okay? So we just go for seasonal. Actually, seasonal might have been working okay, right? But we did monthly. And we said, okay, we're going to have monthly variation in here, and therefore we're going to collect monthly precipitation and average temperatures for that. Okay. There is an open access Thorwell moisture index GIS map for the United States, which basically you just get, and I can give you it's in Google. You can just go over there and click in any place, and it will bring the weather station when they calculated an annual value based on 2 years, like in 2006 and 2025 or something like that, or 2020, I guess. So to compare on that one, and basically those are numbers that you use as a basis for analysis. But we collected from any place, but this place particularly, we got latitude, longitude, elevation for about 10,000 weather stations, information on that, with annual precipitation, annual potential evaporation, 30 years TMI values as well. Okay. So this one is how you calculated that TMI that you used yesterday, right? the TMI that you used yesterday. And again, the third wave moisture index is very old, 1948, when it was postulated. And basically, that was part of the development of a classification of a system for climate condition based on a moisture index, right? And these are the equations that Thornton used for that. Remember that precipitation is easy to get, right? You know, you got precipitation data from any weather station. But potential evaporation, okay, is difficult to get. It's difficult to get, okay? So the potential evaporation, there are equations that were postulated that are a function of the length of the day and an n value, which is the number of days in the month, and the temperature in here, and this one is the mean monthly temperature, okay? And this one can be used for a daily value for potential evaporation, all right? A lot of people, I think if you go for weather station data and you just click, give me the potential evaporation for that site, it might be using an equation like this or similar to calculate that value, okay? So now, we got also for monthly, you know, we can just use the same equation for monthly data. And we can also do it for an annual index, making the summation of those potential evaporations for the monthly data, okay? So this is how you do a TMI annual, monthly, or daily, right? You know, we just, TMI no, but at least potential evaporation. This value here, the A sub T value, is basically a parameter that is a function of the annual heat index, function of temperature. The annual heat index is a function of temperature, and again, it's an empirical parameter that this researcher Thorway collected for every place in the United States, and this has been going all the world. You can Google Thorway moisture index for this place, and it's going to show it. But there are also some other countries that use a different moisture index, right? But it's a measure. Again, it's a measure of the infiltration, the balance between the infiltration and the actual and the potential actual evaporation. Okay, so how we use this data? Okay, we can use it in two different ways. One, we can use historic climatic data. You know, data that we do have is historic, right? We don't know what's going to happen tomorrow, right? But we have historic data to figure out probably tomorrow the soil suction profiles. And this one is important because when you have, again, forensic studies, you're going to have those when you're going to be called and said, okay, I need to figure out what's going on in this road. Why is damage, right? And you're going to make analysis of what happened in that period of time that you have. So we collected average temperature for the month, precipitation, and we calculated a Thorway moisture index, right? Thorway moisture index. How we calculated it, I'm just bringing it here probably, you know. Again, this is that index in there, the Thorway moisture index. This one is an equation that we got out of basically what he published. You know, he get all this equation, he put a map. So we went to that map and we figured out what he did and everything, and we came up with a much simpler equation in here out of the map when this is the precipitation. This one is back in 2001. And this one is the potential evapotranspiration. They were using data from agricultural people, right? So they do have also the benefit of plants and stuff like that. But you know, we modified this one and we just, you know, used the Thorway moisture index with this one, in which we got the potential evapotranspiration in here, calculated with this guy, not with the one that he gave. Okay, and what we did again, like I've been telling you these days, is that instead of having one value, we just did it an annual index, which is an annual index, but we just did it monthly by monthly. We drop January, we take January. We drop February, we take the next one, and so forth. So we run it like that, and we were able to get kind of, more seasonal variation of the Thorway moisture index. Okay. Again, this is a tendency of the environment to to get to that value of total moisture index. Okay, it's a tendency, because obviously, like, everything, if you get more rain, it start going up. If you get more evaporation, it start going down. So this is very empirical. Or you can use it for new and rehabilitated pavement design. In that case, you're going to need to forecast the weather, right? You don't have it. You need to forecast it. In the design guide, procedures that we got in the United States that AASHTO were, what they did is they didn't have any forecast model in there. What they did is they used the past 15 years of information from weather station, and they repeated 15, 15 plus 15 or 15. Whether it's good or not, this government, they don't believe in climate change. I do believe in climate change. All right, so this is the way they're doing. They're having some weather station information in there available. Okay. Obviously, in that case, we do have information from the past 20, 30 years, more. And you can have average values for temperature for every month, average precipitation, and also you're going to have the variability associated with those 20 or 30 years, right? So now you have the opportunity to do a stochastic analysis. And the same thing, you have TMI, and depending on the number of years you have, you're going to have some variability associated with that running TMI. All right. So I'm going to finish the total moisture index, and then we're going to go for the break, okay? All right, so again, this is how we calculated that. We used that equation, and we found this one is for a weather station near Paris, Texas. And this is the kind of data that you're going to get for any weather station that you get. It's very easy to program. That's not a problem at all. Those equations are easy to get and program. All right, I guess that's what it is. After that, we wanted to get the environmental conditions predicted that way related to the suction of the soil that you're going to get at that particular location, right? So that's the second step that you did on your program, on the project yesterday, right? And basically, we're going to continue with this, how we determine that suction envelopes for the changes in water content, or on environmental conditions, and all the way to the depth of equilibrium value, and we use that one to estimate the moisture content variation. Any questions on the thermal moisture index? All right. The questions are there, pretty simple. Again, if you need to program them or something, it's very easy in a spreadsheet or in MATLAB, no problem at all. Or you can use also maps when we have some numbers available. All right, so I'll see you guys. What time it is? What time is 2:30 or 2:30? So 2 hours for lunch? All right. So I'll see you then at 2:30 here. Any questions from online? No questions, okay. So I'll see you guys in a couple of hours. Thank you. All right. Everybody in line? We have more crowd today. Are you guys ready? Have a nice lunch? Anyway, we're going to continue here. Hopefully, we're going to be on the next hour. We're just going to finish for the day. And then you just can go and do your stuff. So, as you recall, in the morning, we were talking about a way or a mechanistic, empirical way to improve over the psi factor that was available in the design guide procedures to incorporate the roughness due to the expansivity of the soil, right? So we saw that one of the requirements for this project was to be able to be implementable in the already existing design guide for pavement analysis, and therefore they didn't want any desire to do water balance at the surface and get infiltration, evaporation, and get all these seep pitch analysis and so forth. So we used the Thorway moisture index. The only thing we did was to modify it to, instead of reading annual indexes, we modified it to be monthly, right? So basically we were able to capture somehow the variability of every year. You can see like probably peaks of high TMI and peaks of low TMI, even if the average value was probably positive for this side, right? In Texas, probably you're going to have a value that is in the order of about +10 or something. But you're going to see some of them that there are some months that were very wet, and therefore the TMI is high. And there were some months when the TMI went even to lower than 0, negative something, which means that the evaporation gained over the precipitation at that particular month, all right? So that always gave us that particular variation of the Thorway moisture index, and in particular more than the variation, the slope, okay? If you have a big variation between the water content, but it takes for that to occur 3 years, right? You probably are gonna have some change, and you're gonna see that change, but it's not gonna do any damage because it's a slow rate, right? But if you have a big change from one point to the next one in a very short period of time, you certainly can do a lot of distresses to your pavement, right? Going up and down. We got a lot of rain and the pavement goes up, go lower and the pavement goes down, right? But again, precipitation alone will not give you that value. We tried with precipitation alone before, like to see if that's the only thing that helps. No, you have to to incorporate also the actual evaporation that you have from the soil. Okay, so this is how we use the Thorway moisture index. It's kind of a practical way to put a superficial value in there that is going to be always, this particular point is kind of your balance point to take water or to leave water. All right. So the second steps was, okay, now we do have a climatic condition, boundary condition imposed, right, at the top. Now we want to figure out how the suction changes with depth, right? The suction changes with depth. And obviously it's going to be suction that are very low and suction that are very high, right? Depending on the moisture content you have in here. And therefore, if you just put all those points for 20, 30 years, you're going to find that for a particular site, there's going to be an envelope, right? That you don't go less than that or you don't go more than that, at least theoretically, right? So we found that envelope, the determination of that envelope. I'm going to show you the model for Van and Houston that we use all these constitutive surfaces Okay, so coming back again to our discussion this morning here, the constitutive surface, if we got something like that for compressible soils, right? For compressible soils, when we have change in void ratio versus either total stress in here or net normal stress or suction. Okay, this one works very well for linear elastic material. So the question is, okay, so expansive soil might not be, right? Because this is something that I told you yesterday. Expansive soil probably behave a little bit more erratic than elastic materials. It doesn't follow elastic theory. Therefore, how are you going to do that? How are you going to use something like that, a surface like that, including those, fundamental stress state variables? Well, you're going to need from the laboratory to figure out new coefficients for this kind of soil. Okay? Now you're going to have compressibilities that are going to be different for this particular soil types. Okay? So this is how you change the material property. You don't change the constitutive model. Okay. So now we were not allowed a final element analysis, right? Like I show you the work that Yasen did on just trying to figure out the suction profile when the flooring conditions were in there, right? That I'm able to do the whole suction profile, right? Well, we were not allowed to run any modeling on that one. So we use a back calculation of important if you do have a salts on the water, or you got, and this is the osmotic suction, the osmotic gradient, right? You're going to have also some change if you just put a gradient, a concentration gradient in there. That is going to create this also gradient going on. For this particular reason, we consider that the soil chemistry, the water chemistry is going to be kind of the same, and you don't have this big suction or osmotic gradients going on in there, right? Or concentration gradient. So this one was eliminated from the model, so we're going to use the two stress state variables that we saw this morning right there. Okay. So this one, volumetric strain, suction compression index. We need a compression index based on the suction, the change in matrix suction, the mean principal stress compression index. If you have a saturated condition, this is your C sub C value, right? The change in normal stress, and that's the osmotic suction compression index, and the change in osmotic suction that we're going to be assuming to be neglected, all right? Yes.
Is it applicable for collapsible soil? Or
For what?
collapsible soil? Is it-
No. Collapsible soils are different animals. Okay, they're totally different. They don't follow this. No.
Coming to your TMI index,
Yeah.
that one, can we somehow consider the effect of the pavement layers?
Let's see how to explain this. Whether you do have an unpaved condition or you have a paved condition, the soil below the pavement is going to tend to an equilibrium condition. It doesn't matter that it takes 3 days, 3 months, or 3 years.
It doesn't depend on the type of pavement.
And it doesn't depend of whether, because if you have a way to get water in there, which is our problem, right? If everything will be paved, then we don't have any problem at all, right? We have no water in. But if we do have a way to get the water in, which is usually about the embankments, right, of your pavement, because you have those shoulders. Sometimes you put some gravel in there, sometimes are open, sometimes are paved, but then you do have the embankment around, right? This soil is going to be tending to get the equilibrium value, right? When you have infiltration rainfall, you get water in below the pavement, and to a point when it starts evaporating, so it's a continuous flux, right? Like we saw on the problem with transient flow. So the answer is, it doesn't matter if you got pavement conditions or not, right? Now, that's a very good question, is because the Lytton model that we're going to see in here that is the basis for this part of the suction envelopes, were created for areas where that they were unpaved, right? So the balance between the environment and the soil was also not only to the lateral flux, but also to a vertical flux, okay? But what we need to understand is that your soil is going to tend to a particular equilibrium value, okay? So you run into that particular equilibrium value. Remember when, and at least on the surface, remember the Pereira model, so we're going to see them in a minute. When you have your suction value versus TMI, right? And we say for a particular soil type, okay? For a particular soil type, if we have this soil in a particular region that corresponds to that TMI, then this soil is going to tend to this equilibrium condition, okay? Equilibrium condition. So let's say this is a granular based material, right? It's a granular based material. And when you compacted that, you compacted it at optimal moisture content, right? Let's say that corresponded to about, if you get to the degree of saturation versus suction, saltwater characteristic curve, the granular based material compacted at about optimal moisture content is about, I always say, between 75 and 85% degree of saturation for all the soils pretty much, right? So you're here, and basically you compacted at that particular suction at compaction condition, all right? So if you get a granular based material with time, and you compacted at that particular moisture content or suction, right? If the soil is located in Arizona, that compacted condition, the moisture content of compaction condition, perhaps is going to tend, the TMI is pretty low, is going to tend to a much higher suction than that, okay? So if we leave everything alone, this soil is going to be trying to go and equilibrate to this equilibrium condition in here, okay? But what happens in the middle road, right, while the soil tends to that particular suction condition, it's going to be some rain going on. So the suction is probably going to go down, right? Oh, I'm sorry, this one is, the equilibrium suction will be higher, right? Alrighty, so I'm going to try to erase this, erase it. Happy with this thing. Here we go, playing here. So that's your compaction condition, I'm sorry, and because it's Arizona, I said, right? It's going to be tending to a much higher suction value. So the equilibrium condition is going to be here. And it might take, it's a granular base, might take few days to reach, right? If there is no rain and the evaporation, keeps pretty much. But it might happen that during that time, you got a lot of rain in here, so this suction is going to try to go down, right? Like the TMI. And probably some evaporation going on because it was a very hot day, and probably it's going to try to go like that. So meanwhile it reaches this equilibrium condition, you're going to have some bumps in the road. And those bumps are the ones that create the roughness of your pavement, right? So this one is for a soil, another soil, exactly the same soil, that has been compacted at the same value, let's say a subgrade material, which is a clay material, right? For a clay material, perhaps, oh no, it's the same granular based material, but it's going to be in here in Guwahati, all right? When that soil, because of the conditions on the environment, are going to tend to an equilibrium suction, which is much lower than that, right? So for Arizona, you're going to see that one, but for Guwahati, you're going to see that this guy is going to go down in here until trying to equilibrate right there, okay? So that's the assumptions that we made. Soil will tend to equilibrate to a condition, okay? Because if you have any way to get the water in and out, it will try to do that. All right, so let's continue with our suction profiles, right? So we're going to have a change in suction in here, because at the surface we're going to have this condition. We're going to have a wet condition, which is going to lower our suction. sometimes going to have a dry condition and so forth, right? There are going to be points where are extreme to that one, and there are going to be points that are going to be in the middle, right? In the middle. And also they're going to be changing with depth to a point in which, it doesn't matter what happening here, this soil in here is not going to feel it, all right? The famous depth to equilibrium suction, right? So what are the parameters we need for that? We need the change in suction at the surface. We need the minimum suction value or the wet suction, and we're going to have the maximum suction value, the dry suction, and we want a function because we don't have a final element analysis to do what we saw yesterday. So we're going to need this change in suction with that, all right, change in suction with that. So in here, for example, at this point or this point or this point, in here is going to be applying two stress state conditions. The suction value that you have, okay, plus the overburden pressure that you have in here that represent your net normal stress, right? If you go down, you're going to have perhaps the same suction values up to a depth, right? But you're going to have a much higher compressibility or movement of the soil due to more overburden pressure, okay? So this envelope represents somehow, that's why it goes down also, represents some of that, okay? But let's talk about the suction envelope in here so we don't get to deviation. Oh, I had done some. So again, these are the equilibrium suction envelope parameters that we need. We need the equilibrium value is the one that corresponds to the suction value at which equilibrates with a particular depth, right? There is always a point when the water content is not going to change more because of the environmental properties and that. And again, we're going to need the depth of equilibrium suction that we discussed yesterday, okay? When basically the change in the dry suction and the wet suction is not going to be greater than, let's say, you can put a number. You're never going to find something that is absolutely no change, right? You're going to have in here some variability associated with that. We put a value of 0.2. All right. And the seasonal suction envelope parameters, would I show you the change in suction, the minimum and the maximum. You're going to say this one is the same, but what I'm talking here is that you're going to have some skewing, right? That's not a beautiful thing like that, a cone, okay? You can be more on the right-hand side or on the left-hand side, depending on the side.
Ma'am, can you please go back to that?
Sure.
Here in that equation, sigma F and sigma I, that is a normal stress. Overburden stress. Sigma F and sigma I. Okay. The equation, second, third.
Yeah, this is the change.
How you differentiating sigma F and sigma I?
Oh, this is the same thing that you do in compressibility, right? The change in volume for your compressible curve, let's say like that, all right? So you're going to need an initial value and a final value, right? And you're going to need this range in order to figure out what is your change in void ratio, right? Okay, so this.
Like if we take an example, it's like understand the volume change, it's like in line loading. So already we have the pavement the stress is the same. The overburden stress doesn't change with line.
Exactly. The normal stress that you put in there is going to be constant, totally constant, okay? So what happened is when we give, Danish, just give me 1 second, I finish the thing. When we give a practical engineering, like, okay, I'm going to be making a slab on ground for expansive soils. And we go to the laboratory and we do a free swelling test. And we tell, okay, this soil is going to be, the expansivity of that soil is going to be 13%. And then they're going to need to work with that in order to do the slab on grade, right? This is a maximum value. This is a maximum value that we get in the lab. That's a limit. That's a limit value that we have, okay? usually what they do is they assume that this value of swelling is going to be the same at the top of the surface or all the way down to 5 meters. And that's a big mistake, right? It's very conservative. The slab, will not fail, obviously, because you're putting a lot of money in there, which shouldn't be, right? Because actually with the overburden pressure, you're going to see, this is the envelope, your overburden pressure, because the change is much smaller in here, the compressibility should be smaller right there, okay? So that thing varies all the way down with it. So in that case, this one is not been taken into account yet, okay? So I think I confused you, all right? All right. So this one is only the suction envelope that we observe in the field for that one. So let's go to the next step because I'm going ahead of myself. Okay. So that's right. So what happening here is that envelope in here basically is independent on the overburden pressure so far. So we're going to be putting that in a moment, right? The only thing that is a functioning here is that as you go down deep, the environmental conditions are not applying anymore, okay? And that thing can start getting down and down. I'm getting ahead of myself in here and get you confused, okay? All right. So let's keep with the suction envelope, okay? We keep the suction envelope to define the maximum and the minimum values at the surface that the soil will be subjected to due to these weather conditions, okay? So in order to define that, what do you need to define that? Well, again, I told you the depth to equilibrium suction, the equilibrium suction value, the change in suction at the ground surface, and the skewness representation, okay? Because there's some analysis that says, okay, this one is not a nice cubical thing going down. So we use a suction envelope that was postulated by Van and Hirson in 2021. They went over 40 different geotechnical sites studies in San Antonio, Denver, Phoenix, and Mount Park in Arizona. And also they collected literature ranging from all the way from the 70s to 2018 when he graduated, right? And based on that, they basically work out, how this suction varies with time for different soil types and in different regions, wherever they were located, right? So the suction envelope, I just put two things together, I'm sorry about that. All right, so the depth of the equilibrium suction, you already saw that, right? The depth to equilibrium suction, they find out, despite they put together correlations with soil properties, with combination of properties and TMI, everything, they found out that the TMI was sufficient and enough to represent the depth of wave, okay? This is, again, when you see all these numbers like this, is empirical, right? It's empirical correlation. And this found this one, but the correlation was actually very good with the data they found. The data from their study is called the surrogate, this study. So they have a lot of data in there, but also data from the literature, okay? So also the equilibrium suction value for so I'm signing in here, right? The equilibrium suction value, okay? So what was the equilibrium value for a particular place? And they also check many different correlations with the data they got, and they found that the best correlation, although the R-squared is kind of weak, they found out that the equilibrium suction is going to be a function of TMI, and that was the best thing they were able to get with this data, okay? It's not that bad, actually, for geotechnical engineering, believe me. It's not that bad, okay? This is PF. PF is nothing but the log of suction in centimeters, right? This is a measure of suction.
Did you try bringing in some soil parameters?
Yes, they did. They did.
Does it give a better?
They didn't. They didn't get any better. Well, if they improve a little bit, they were not worth it trying to that. That's exactly right. So they tried different. There's a whole thesis about it, and all the analysis that Van did for that. Jeff Van, and actually he's a very successful consultant in town. So he has access to many big equipment and many sites, and that's why we were able to get very nice data set for that. What are the limits to the potential suction change? The delta sigma at the top, and for that they also went and checked some data from the literature. The data they found the R squared to be about right, and basically that limits the potential change in the suction at the surface, and it was important because we needed to know how much that's going to change. We don't want to go crazy, like if we have a very bad month, very dry or very wet. So they also found this one to be a function of TMI. And also they found a parameter that accounts for the asymmetrical nature of the envelope. They based their work on the Oveni and Long, which in 2007 they demonstrated that the asymmetric soil suction envelopes are expected. Before 2007, everybody was using a very nice envelope. And some of the good work that is available is from the Australian people and South African people on that one, okay? So that was a step forward over the South African people. They incorporated a parameter, which is what a total of suction change in the surface. And basically, that value was a deviation from the equilibrium suction, okay? Over the whole range of suction between the dry and the wet. So it's an R value, which is a percentage from one side, right? From the wet side on what can, how much skewing you're gonna get. All right, so we got, these points, the delta sigma, we got the equilibrium suction, we got the depth, and now we need the function. We need the function to go down, all right? For that, they went down to the literature and they found Mitchell 1979, and this is being used a lot by the Texas Department of Transportation. They do have a function in which they have 3 parameters. Basically, if you find those 3 parameters, you should be able to get what is the suction at any depth, okay? By knowing what the equilibrium suction is and what is the change in the suction above. And those 3 parameters were in here, right? The Z, the N, and the alpha. All right. So they went, and because they knew what the suction was at the end, because they took a lot of water contents and they know how much, saltwater characteristic curve. They knew the suction variation with depth and what was the envelope. So they went, and with the data they collected from those 40 sites, they calculated those parameters. Okay, but calculated those parameters, they found an equation for that then they could use for any other type of parameters, right? For any type of soils. So that's how they got that one. The weight and the dry limits, the ground surface, the maximum and the minimum suction values were determined with this value, with the skewing value in here from the deviation from the equilibrium suction, and also the dry is going to be the wet plus the delta sigma that they found in there. So with that, they were able to do, and this equation actually, there is a very beautiful, a lot of work by many years by Mitchell, in which he ran Richards, it's a Richards equation, okay? And they ran multiple, simulations, and they figured out how to do a closed form solution, okay? So glad we have that, because we didn't, we were not able to run Richards equation on that point. Yeah.
This particular equation, this was based on the field observation or you performed some lab?
Richards, no.
No, this one.
Oh, the calibration of that equation, yeah, for the field data. Yeah, field data.
Performed on lab control test, laboratory control test.
They did all this soil that they took from those 40 sites, they took it to the laboratory and they did saltwater characteristic curves and all of that, okay? So what they did is they figured out in the field, we didn't take suction measurements, they didn't take suction measurements. They went over there and drill, right? They core and they drill and they figured out the moisture content, okay? The moisture content on this place, right? They did that and they used the same 2 or to go and check again 3 months later, 6 months later, 1 month later, right? And they did a work about 2 years. They were figuring out how much the water content changes, and you can see the data that they obtained. It was pretty neat. Okay, they obtained, it's not, they just did water content determination all the way down, right? They go ahead and took samples, and they figured out how much the moisture content will vary at that particular site.
And they relate with the suction.
Exactly.
From
From the
SWCC.
SWCC.
This SWCC, did you consider any load effect or it's a free condition?
No, we did consider load effect. The questions are, okay, how we go from the water content that we got in the field to the suction values, right? To figure out these envelopes to be able to calculate those values, right? So in this one, if you use the pressure cell, actually you have the opportunity on the pressure cell. You do your air entry, high air entry stone in there. You just put some load in here. You just put everything down on the box, and you have a way to get load applied to this one, and put the value on that particular. That was me. Sorry about that. No, I think.
It's fine.
Okay. So we got this thing, and we were able to figure out saltwater characteristics corrected by volume change due to the different overboard pressure.
I'm more interested to see the variations with under the overburden stress. How that is going to impact this profile.
Interest on the variable.
That the suction variations that we were talking about. Suction and
These guys,
does it get influenced by the overburden stress?
the water content, no, supposedly not, right? The water content is not, but the suctions do.
Because whenever there is a change in the suction value or saturations, under the soil may undergo volume change. So eventually
Yeah.
that is going to impact the
Yeah, but-
SWCC.
Okay, so we're talking about the saltwater characteristic, right? And you said, okay, we got water content in here, and we're going to get suction values right here, right?
Because it's an expansive soil.
Mm-hmm.
So whenever there is a change, you have some loading. It's volume
Exactly.
will change.
So you took that sample that was very expansive, actually. You took it out from here. You took it out from here. You took it to the laboratory, right? And basically, what you have to do is you need to consolidate or just load it again to the overboard pressure that it was experiencing in the field, right? So basically, you return the stress history to that point. To that point.
My point is when you are trying to get all the suction profile here, suction and as you are going deeper, overburden stress is changing.
Yes.
Right. So I just wanted to know from the lab when you are overheating with the suction, field you have measured the moisture content.
Yes.
Right?
So we measured the moisture content. We took it to the laboratory to the SWCC on that sample that we took from there. So in order to do that, we loaded to the overboard pressure that we got at that point. You load it to that overboard pressure, and you eliminate any expansivity that you get due to that unloading that you had to do. So you load it again to this point, and then after that you
And
do
we need
the
to
equilibrium
calculate
analysis.
the number of SWCC on the different overburden load.
Yeah, so you took a sample in here, then you took a sample in here, and you do the set. You vary this normal stress on here.
Number of SWCC.
No, it's one.
One.
It's one, but corrected for volume change. You see, any value, it could be higher, low water content, whatever you get in here, but the value is already corrected by volume change. Okay, at least it incorporates, it actually is now independent of the overboard pressure because you put it in there, right? And then, therefore, you are going to be having this. Great questions. So that's how they were calculating those values, and they were able to use the Mitchell equation for that. All right. They got at the ground surface, they have the minimum and the maximum values were determined with the values they found based on TMI. Then they use the boundary condition for the suction value at each depth, because this is the question that you have, suction at any depth for the wet, low suction, the wet envelope and the dry envelope. They use the equations in there, and it should be in here somehow the Z value, right? The depth, right here, right? Right here, the depth value. All right. So you do have now the suction with depth. So that's how we create those envelopes. Okay. Now the next set of steps, it was the generation of the changes every month. The changes every month. So we know the big picture, what's going to happen with the years on the dry, on the wet side, but now we need all this, and for that we needed to figure out how to calculate that time varying suction, right? The time varying suction. The first thing we did was the deterministic approach, right? We only have data from weather station, past weather station data. So we were not forecasting anything on the weather conditions. We have only the data from the past. So that thing you can use for case studies, forensic analysis, calibration efforts, or so forth. Okay. The stochastic analysis, on the other hand, when we have randomly generated monthly TMI, you got to estimate that based on historic data. Then we are able to do an associated variability with this particular data set, right? And this case, this analysis we use for design future pavement structures, okay? Because we do have an stochastic analysis for that. I'm gonna show you how we did that. So the time varying suction at the surface, you've seen this model before. Actually, you use it in part of your exam for tomorrow. It's based on the work by Pereira. The two models were available as you check the granular-based material and the sub-base or sub-grade material for coarse-grained soils. I already talked about how we obtain these models, visiting also a lot of sites in the United States for this. And basically, this one is kind of the equilibrium suction at the surface, right? Or near the surface, very near the surface. We didn't go deep. We didn't go deep. But we included, actually we went deep. But there were two things that we had in here. We were deep on this analysis, but also the Van group also went deep, okay? And they figured out the suction at equilibrium. So what we did is we used Pereira models to estimate the suction at equilibrium at the surface, okay, how that varies. Then we used the model to go to the suction at equilibrium at depth using the Van model that we got in there, the depth at this. So that's how we combine the two models, or the two informations available. So you know how to use this one, depends. Anybody has any question on the homework assignment for last night? All right, while we're here? All right, so this is what we got, an equilibrium value for this. So we do have the Torway moisture index, and when you have the Torway moisture index and you apply those models, you were able to get now the estimated soil suction at the ground surface, okay? It's just applying those models, right? So from the Torway moisture index, which is this guy, we were able to get now the changes in the suction due to those changes in the environmental conditions, okay? Now, there was some adjustment that we have to do at the surface, because remember that the Van found an envelope, and some of the data that we did with the Pereira went out of the envelope, right? Because we did it for different soil types, different stuff. So basically we accommodated the changes that we got for the Pereira within the envelope that the latest group of researchers have done, okay? And this adjustment of the suction variation was, using the Van. It's almost the same, but it was a little bit of tweaking there that we did for that. When it's just a small equation here, to be able to see that we were into the envelope, within the envelope. Now, the problem in here is feeding the surface suction data, because now you do have this guy. Okay, you got this guy all over the place, suction going up and down, right? If we have only temperature, that would be a very nice sinusoidal stuff, right? You look at the temperature, it usually goes up and down, very sinusoidal depending on the climate conditions that you're going to have and the seasonal variation. But when you do have TMI, you're incorporating the rainfall in there, which is the tough thing to do. And now if you want to put it in a model that is a continuous model, you're going to be putting all this crazy data into a function, right? So sinusoidal or periodic suction is not going to work. It's not going to work at all. So we jump into the Fourier series, right? And we start getting into 1 second order of magnitude, first order Fourier fit will give us, this value here. The 8 order, will give you a little bit more the jump. We were trying to catch up the jumps, right? The peak points that will cause the problems in the road, right? We don't want it to smooth the suction. We want it to be as precise as possible as the data that we found in that one. And then adjusted, so basically we went and 1 to 8 orders of magnitude, and then we were able to do in MATLAB a code that will adjust the end value of the Fourier series to the one that was the better fit for that. Okay, so that's another work that we do. We improved the 8 order of magnitude. Did we lose them? Okay, so we'll give it 2 minutes. Oh, they're there? Okay. So we did a lot of work, there was a lot of discussions about that until finally we were able to optimize that order, Fourier order, by creating an algorithm that optimized that thing. So sometimes it ended up with a Fourier number of 32, sometimes with a Fourier number of 18 or something like that, okay? But in that way, we just save time in not running this one to a very high Fourier number, which is going to create a lot of data management. And we did a very good job. We started with a minimum order with the red pointing here, but if you see the blue lines and the natural order of magnitude and the little points we got, okay, this is pretty good. Now we are able to catch every single thing with just an equation, all right? So we did that to figure out what was the variation of the suction at the surface, okay? Then we used the Mitchell equation to model the suction profile for every time step down. And again, this is the equation. This is the equation for that salt suction or forward pressure in here. So you see the first month we got this particular location, and then for the second month, that changed, and then we use the equation, and that thing goes into like that. And we did that for for 12 months, and for that for many years that you want to do. Okay, so that will run 10 years, and that goes up and down. You go to the largest but now we were able to capture all of these changes in the climate by changes in the suction envelopes profile that we got. Okay. Then we did adjustments, and here is what your Danish answer is. Okay, we accommodated. First of all, remember expansive soils are unsaturated soils. Usually occurs in areas when you have groundwater table at a greater depth. Okay, obviously, if you have groundwater table that are shallow, you need to cut down the suction to a 0 value at that particular point, or you need to merge the capillary rise with the envelope in here. This is a word for you guys, okay? I don't know, we're gonna do that, but this is something that we have for next, right? Future research recommendations, right? What we also we have nearby vegetation that creates extra suction values, okay? So probably those envelopes will change because you have very aggressive trees around that is going to take a lot of water, right? Or some other stuff like that. So there are many things that we can do with this model. Some of these roads that have a lot of expansive soil, they put moisture barriers, right? And they're vertical. So now this is going to delay, right? This and the envelope might be narrow in that case. And also we need to adjust the function because of the net normal stress that we were talking, the overburden pressure, right? And that's how we incorporate the second stress state variable. So the overburden effect is fully considered, and what happens is, if you have no overburden, this is your free swell that you're going to have in there. But as you have overburden, that thing is going to start going, lowering here and lowering here. And now the swelling strain is going to be lower and lower, right? Because and as a matter of fact, if you go to a certain depth, that's another one of the nice discussions this morning, this kind of model will tell you that that soil that used to be expansive above can collapse when you are down. And we've seen collapsible soil, collapsing soils or, compressible soils or compressing soils that are expansive in the laboratory as well. Okay, so that happens in here. So this one is for example, the layer when it started evaporating, the flux was down, and probably it's going to be very small change in the middle. Nevertheless, that's why we got the cracking forming, because of the flapping. And basically, the change in the expansivity is much less under the center of the pavement. Okay, and this is a model that was also put together by Litton and his group of researchers back in 2012, I think. And this one basically created an equation that if you knew how much was in here, you were doing, how much, expansivity you will be allowed at the center of the roads. Yeah, so I'm just talking about that rigid foundation, and I'm thinking about that, but we'll include that later on. Okay. So some validation studies were done. We started with that. These are measured data. We see that they were mostly on the dry side, and we were just, not being very good. We're being okay for the deeper section, but not on this side. So let's start adjusting a little bit more until we were able to get this on the at least looking at in here. And what I'm looking in here is, okay, what happened this particular day, right? This particular day. This is my model, and these are the measurements that we had in the lab, in the field, right? So at least gets the right tendency to go down at that direction. Okay, so it's obviously a lot of variability associated with that, but we were able at least to get into the ballpark of those predictions. Okay, now we got the suction envelope, we got the suction profile, we got the changing suctions with time. Now we need to translate that suction into volume change, right? Which is the important part of it. So how to do that? So the first thing it was, like I said, we need a compressibility index, right? Anything that you do, whether overburden, whether net normal stress, whether effective stress, for suction, you're going to need a compressibility value right there. Okay? So there is a very famous work done again by Kovar and Litton, McKee, 1989. This is Colorado, U.S. Geological Survey. And they did that one for, again, post-tension slabs on expansive soils. And basically, there are a set of graphs that relate the suction strain, or the suction to volumetric, the total suction to volumetric strain. And basically, it is an empirical set of graphs that takes into account the soil properties, right? If you got more PI, passing 200% clay, you use all of these parameters as we saw yesterday in our lecture for problem soils, that you can actually estimate some volumetric strain going on in there, all right? So that work is available and is there and is being used. That this is what is being used for the last, I don't know, 40 years, 19 to 25, 35 years, 40 years in the United States, mostly in Texas, where we got in Colorado, we got a lot of expansive soils. And also, one of our students as part of this study, Mohammed Mosawi, he basically took the soil water characteristic curve, right? And he started measuring the change in volume just to the applied suction, okay? So we put in that cell, we put an LVDTs, right? And we start changing the suction, and measuring the volume change for all those expansive soils that we had in-house from the previous study from Van and Houston, okay? So we did that, and he was able to find, the change in void ratio versus suction as you go that, and they translated this one into the strains versus suction, and basically they were able to find, at least a compression index, but at least, a relationship between the change in void ratio and the change in suction and the change in normal stress, okay? And he added the WPI, and I don't have the R squaring here, but it wasn't bad, it was good, okay, with the data we got. So we got passing 200, PI, and the two stress state variables in here, right? Okay, so it's a combined compression index, right, that takes into account the two of them, because we are not using the constitutive surface on the model, okay? So we calculate the volumetric strain because we got now the compression index from Bob Litton, but again we do have this one. We haven't implemented this one in the model, and with that, this one, which is our mean principal stress compression index, which is the one that you know, right? C sub C over 1 plus E naught. And the other one we neglected. All right. Calibration was done for a very small amount of material. This one finished in about 2 or 3 years ago. And what is the problem? The problem is we don't have measurements of deflections pretty frequently on these soils, all right, on this particular. So we went for data from the long-term pavement performance, which is a big database of data that we got in the United States, and figured out deflection information for places when we know that the soil is expansive, okay? And some of that was caused by expansivity, right? So we went for the very corner, that it was the one that it was just flapping out, and sure enough, we start adjusting to some of the values that we found, that we calibrated. So we developed statistical correlations of measured versus predicted. Not very good, like you say, an R squared of 0.61 is, okay, this is for asphalt pavements. We used 58 calibration points for that, 41 for the AC sections, and 17 sections for the pavement, rigid pavements, right? And we were able to get a much better correlation with this. And obviously the recalibration is in progress because we need more and more data for doing that, right? These are kind of poor correlations, but the framework is there. So in that way, we were able to figure out a volumetric strain for a particular region and for a particular type of soil. Now, what if we need to predict what's going to happen in the road, right? What if we need to incorporate this one into the design procedure? The road hasn't been built, right? And we need to give a good estimate of what we're going to be expecting if you do that one on this expansive soil. So this one is when the stochastic solution comes into play. And stochastic means, that will allow you all this variability associated with the climate and material properties that in turn is going to behave as the variability associated in your suction parameters, right? Your suction envelopes in here. And not only on the suction envelope, but also on the equilibrium suction and so forth. So the variance associated with the volume change response is what we consider to be representative of the roughness experienced by the pavement at that particular point, okay? Because it's the change, right, that creates that variability, okay? Again, we use Monte Carlo, which is simulation. When you do a lot of simulation for that, we start with Monte Carlo. But again, when you deal with climate, you need to be very careful with Monte Carlo simulations. Why? Because stochastically forecasting of time series is not a very good idea for that. Why? Because the climate that we had today, Friday, is a function of what happened yesterday. And it's a function of what happened last week, okay? So the climate today is a function and dependency on the 2 or 3 days before, or the 2 or 3 months before, how the climate is going. So you just can randomly generate a number for PMI, right? Or for infiltration, for temperature. So this is what happened when you put Monte Carlo simulation in there. You get the average value there, but you are all over the place. When you consider time series data, there is a model that is called Markov chain random walk, okay? Basically, it takes into account for this particular simulation what happened yesterday. So we can take 2 or 3 days before, and if you see now the estimation of the climate is going to be a little bit more, centered, and it's going to be more adequate for and that's what environmental or weather people do, right? They just do forecasting with that kind of model. So that's important, and that improve a lot our predictions on that and what we will get. So we use that, and again, you can predict TMI before if you have the data, and there is a point when you want to forecast, okay? So you start just making that prediction on that. We try different parameters, like for example the changes in TMI. For the temperature, it was very good. Temperature is very easy to predict changes in a long run, right? Not what's going to happen tomorrow, but in a long run, you're going to be able to predict very nicely for the temperatures. For the TMI, was a little bit more rough, but if you can see, just every one of those simulations, we're going around, right? What we will expect. We have no idea what is there. But so you just create many of those simulations until you get values. Right. So how we incorporated this model that now we do have a value for the volume change, but also we were able to stochastically estimate everything that I've been showing right now, right? The temperature, the infiltration, then the TMI, right? And now you got variability associated with that, all the way to the suction profiles, soil properties. Even we included variability for the soil properties, okay? Because even if you go and I tell you, 3 of you, please measure this PI of the soil, you're going to give me 3 different numbers, right? So even associated with the laboratory testing, you're going to have some variability associated with that, okay? So we incorporated all this variability into this stochastic model, and basically use the variance and the standard deviation associated with the volume change response, okay? That will serve as a surrogate and replacement of that famous psi factor that it was there before, okay? I didn't bring this in here, but this work was done in conjunction with Case Western Reserve University, and they did a model. And this model was, that was easy because the temperature model was already created in the guide. And they did a frost heave analysis, okay? So we were able to also create values when you do have frost heave soils. We were able to create a psi factor for those values, okay? So this one is for the ones that we created. Again, we're just trying to change this guy in here, and just by the values that we're getting, and basically that's the same. Like we can do it in overlays, the flexible pavement with overlays, rigid pavements, concrete pavements. All of them have the psi factor. Okay, so we were able to modify that one, and even though if we don't include a slab theory, for rigid pavements in there, we were able to empirically incorporate the rigidity of the pavement by just working with the right equation that they have for pavement analysis. All right. The variance found to be provided the best fit. We tried standard deviation, variance on the slope, many factors. We use the sum of the square residuals drop more than 75%, the sum of the square errors also more than 50%, and the R square increased from 53 to 78%. So we did have many, until we found out the best combination. We used 171 data points, IRI measurements in the lab, in the field, real IRI measurements on places where expansive soil, and the IRI they measure in the wheel paths, but they also measure values close sometimes. That they do different ways. But we did that. We used the R square, the variance, and the prediction IRI with the measured IRI was very good when we incorporated the variance associated with that result in there. So if you see, this is another word, right? It's not modeling, it's not very fundamental, but it is based on more mechanistic analysis than just to put 3 values in there for PI passing 200 and precipitation on that, okay? So these models are now being incorporated into the design guide, right? And we got models for soils that are also frost heave. Now, there one student in Case Western that are trying to figure out soil that are frost heave and expansive at the same time. To see, we just combine it. I don't know that's how that's going to work. Empirical regression analysis model performance. This is we compare the new IRI model for AC payments with the same equation that we got before. And we got this is the site monitoring versus the model. And this one this one is an R square of 0.63, improved, the variability associated from 54 to 63. So at least it improved a little. I'm telling you, this is a very good prediction for IRI. This is very variable that we got here. So this is what I got for you today. Okay, what time it is? 3:36. Do you guys have any question with this? At least the way we did stuff. Rahul?
When field deformation measurements were done for volume change, parallelly there would be traffic going on, right? So there would be that primary, it is based on the age of the pavement, it would be either in the stage of primary or the secondary compaction. So
Okay.
so the data is coupled with both traffic movement and the soil character.
And you're talking about the data we use for the calibration
Yeah.
of the deformation part of it? Yeah. So if you check a pavement or the LTPP, what you're going to have in here is, that's your pavement, right? And you're going to have deflection measurements at the crest, deflection measurement on the outside wheel pad, and inside wheel pad, more than me that. And they also have one very close to the shoulder when there is no traffic. Okay, so the ones that we used were those guys in here. Okay, which will at least avoid, the deformation associated with the rutting condition that you're saying. Good questions. They have like 5 or 6 measurements in there, so we were carefully with that. It's very difficult to find out, it's also a lot of money to be able to estimate and to put strain gauges in there to figure out how that soil will change. They don't do that. Any other good questions? Bad questions? Questions? All right, guys. All right, tomorrow we're going to come here a little bit also for a very practical applications of geosynthetics. Okay, we're going to be looking at that, and I guess you're going to have your Claudia. ceremony on that.
One question.
Yeah.
In the beginning, you mentioned about trying to understand about the recovery time.
The recovery time.
Whenever
For
you talk
recovery
about-
time after a flooding condition, moisture changes. Okay.
Do that, like, have you worked on that to estimate the recovery time post inundation or flooding event?
Okay. So I don't have any. I do have in here. Well, what I showed you last time was was a table, and I think I can find it in here really quickly. I'm not going to close this one in case somebody has any questions on that. Okay. Oh, this only has day 4 in here. I used to have all of them. Do you have day 3 lectures? Yeah, great, thank you. Oh, here we go. Silly me. That was day 3 or day 2?
Not
Till day
sure, the
3.
very beginning you.
Yeah, it was the
Yes.
first one. Yeah, thank you so much. All right, thank you. So that was the example we had in here, right? Here we go. So if you check in here what, we're at this stage, this is in progress right now. But what we have in here are the different soil types and the changes in resilient modulus or moisture content or recovery, right? With time. And we run this one for about 100 days. We can have run this one for a year, something like that, okay? But a road will never allow us to open in a year, even if I tell them that thing doesn't recover, right? Because they need to open the road immediately. So basically what we're going to be using this kind of data that we're getting is to inform the state agency how much loss in the steam net you have, right? And obviously we did, we did a little bit more at the beginning, like the first 1 or 2 weeks, right? Because this is, and we find out that, for example, for the first 2 weeks or the first week, okay, depending on the soil type, you either lost 11%, 17%, 13%, but some of those soils you can go all the way to 50 or 60% reduction in a week, right? And it could be that is progressing towards that. This one is keep going. This is still being reduced after 50 days, okay? So obviously you're not going to, I'm not going to suggest them to open that road if you do have this kind of soil flooded, okay? But what's happening here is they need to make an estimation of how much is the 10% and how much will that affect the traffic load. We can do that with a couple of methods, all right? The old Ashton 93 method has an equation in there when they said, okay, this is the number of repetition that my road is going to maintain if I got this resilient modulus, if I got these soil properties, and so forth, okay? If I change the resilient modulus by reducing 10%, they immediately will know how much number of repetition they're going to lose on the road, okay? This is one way of checking. Another thing is how much capacity you're going to be losing on that, and they can figure out how much thickness they're going to need to put extra if they want to have. So they have ways of knowing, okay, how to incorporate that reduction into the real capacity loss of the pavement at this point, okay? And Ashton 93 is an old method, but a lot of people use that one. Or you can run, a design guide, a new design guide, and basically figure out how much riding you're going to get if you just lose this amount of, if you reduce resilient modulus, right, to the maximum reduction value that you see here, and figure out how much time on that one. This is for the loss of capacity. for the opening time, you basically, for the recovery time, you're going to tell them, okay, look at this. This one goes to 53%. So I'm very sure by the 5th day, you lost only 20%. So probably you're going to be able to start getting small trucks or something like that. All right? If you have a low volume road, probably that's not going to be a nice thing to do. But if you have a high volume road that they're looking at the number of big trucks that goes to that one, probably they're going to be able to get cars around that with 20% reduction with no problem. Okay? So this is something that they, in their experience, they will know where to open the road for that. But we give them a tool.
Okay, basically, like, do you assume it to be elastic nature? Like, whenever there is a loss,
What do you mean? Sorry.
that modulus behavior, do you take it as elastic response? Like, once.
Yes, this is elastic.
Elastic
This
only.
is a resilient modulus.
Okay.
This
Like,
is the
when we talk
modulus-
about loss of 50%, 60%, so in that case.
Exactly, it recovers.
Okay.
You will recover exactly. So, as a matter of fact, the equation is an elastic model equation. Yeah. So that's a good question. I need to check that out
Okay.
because then we have to check into what kind of nonlinear relationship we got between the modulus and the water content, right?
Right.
And these are not,
Because
they are non-linear.
the strain level is very high, 60%.
60%.
The loss is
very
60%.
high, right. So what you're saying is, no, but again, the resilient modulus of the soil is the capacity of the soil to withstand that number of repetitions, right? And
Yeah.
this is the recovery strength that they get. All right. Now, in order to do rutting is already when you do have failure, right? When you have a shear failure. You basically do a test with a deviator test until you fail the soil, and you can count the number of repetitions that you need to fail that soil.
Okay.
And that becomes into the elastoplastic behavior, right? Right. But this one is the resilient modulus of the soil, is the soil that, and obviously you just get some repetitions that are creating some ruts, but not a failure, a total rut failure. This one are repetitions that the pavement will be able to withstand, the soil will be able to withstand.
Okay, ma'am. Thank you.
Yeah, but this is a good question, because actually what you got in here is that change in environmental condition as a function of degree of saturation. Okay, and this one is kind of a non-linear, right? Non-linear function, right? So if you have an A6 soil, which is a WPI probably about 20 in here, right? So if you went from a value of optimum condition, and the reduction was because you get all the way to here very saturated, right? You got very saturated. You need to dry it again, but you're gonna go in here. But I guess it will recover. The analysis is that resilient modulus mean, elastic modulus. Good questions. Make me think about that. Any other questions? Alrighty, so that's all I have for you today. So I'll see you tomorrow, right? And we're gonna be finalizing here with the lectures.
Excuse me, Prof.
Yes. Any questions right there?
I am on this side. So actually this is from the lecture number 9. Lecture number 8 from today's class. Could you please explain the slide number 22, which was related to extended Bohr-Coulomb failure in weather?
Alright, so from today's lecture,
Lecture number 8, slide 22.
alright.
Sorry.
Yeah, I'm looking at this one. Yeah, the shear strength.
Is exactly extended Bohr-Coulomb failure in weather. Shear stress versus the net normal stress in the left we had. So you were explaining something about the effect of suction. when we were calculating phi v.
Oh, yeah, that was the discussion this morning.
Yeah, I can show you a place. We just a moment.
What slide did you mean?
This slide number. Can you see?
Let me check. Okay. This is when we get now, this one is the saturated condition, and then we get into the extended Moore-Coulomb failure envelope for unsaturated salts, right?
Yes, this
Correct, correct.
Here we go. All right, so what I was telling in here is that if we want to extend the Moore-Coulomb criteria to account for the unsaturated salt condition, is that if you just check this graph in here, the first plane that you see at front is going to be your net normal stress versus shear stress at zero suction. Zero suction means this plane is the saturated plane, right? Is the saturated plane. Are you agree? Do you agree with me? Do you understand that?
Yes, yes.
So all these more circles that you got in there represent, get a failure surface that is for the suction equals zero condition, right? Suction equals zero condition. Now, if you start increasing your suction, basically what happens is that the Moore circle is going to be bigger. At the same confining pressure, you're going to have that your suction, the Moore circle is going to be bigger, and therefore your shear strength is going to be higher. And how much higher it is? Well, whatever contribution of the suction to that. That for this particular model, Fred Land uses a linear increase in the effect of suction over shear strength by considering the tangent phi being here multiplied by the suction value. So as you increase your suction, your failure envelope becomes pretty much, if you have the saturated condition here, and if you just use one value for phi b, it's going to become parallel to that one, and it's going to be increasing that amount. This thing in here is going to be the contribution of the pore air minus pore water pressure times tangent phi b, right?
Correct.
Okay, or the tangent b. So, is that clear now, or do you have an extra question about that?
No, this makes things clear.
Okay.
But like when we have to include that thing in case for the case of repeated load, right? So in that case, suppose we are going to use for the constitutive model, which varies linearly with the depth. So in that case, how we are going to implement this Fuller envelope?
Okay, repeated loading. This is for a static loading conditions, right? This is the theory of shear strength for static loading conditions when you applied a confining pressure and when you applied vertical stress or a loading stress. So how the shear strength applied to repetitive loading, right? Repetitive loading conditions. There are more theories that relate to that one, but in pavements analysis and design, there are a different model. They don't use Moore-Coulomb models. They use, and I don't have the models in here, that when you do have a lot of repetition, and we were just discussing that, a lot of repetitions as a function of your deviator stress, and that thing is going to be increasing until it fails. Okay? The model, I don't remember, is like the number of repetition is equal to deviator, over the, so to a particular value here, or I don't know, a B or something like that. I don't remember the model that they use for that. And basically that represents the number of repetitions that you do have in order to fail to cause rotting in the soil. That's called rotting or permanent deformation, right? But I'm not familiar with that. This is very pavement related stuff, and I don't know. But definitely they use the deviator stress. They use, I guess the Coulomb failure is going to happen, right? You know, it's just going to be something like that until it fails, right? So the thing is, now instead of loading it to find out resilient modulus, when you do that, the loading to be close, not too close to failure, now they're going to be loading it until they get failure, right? And I guess the criteria will work and will apply, but they don't use that when they use an equation related to the number of repetitions to failure. But I don't have the equation in here. It must be, you know, I don't know. Do you guys any payment guy in here that tell me that? I don't remember exactly the equation, but there are some models, actually the little model for permanent deformation for soil. And it works also for confining pressure for, you know, consolidation. Do you have that, Rahul? I'm here a payment expert, so I'm going to give it to you.
So the first part takes into power law.
It's a power law.
And then the second part where it is exponential, the secondary compaction where the deformation is very high.
Okay.
So it takes exponential.
So you got something like that and then go like that. Okay, like a flow number for the asphalt or something.
Flow number. So the first section is the power law. The first part of the equation takes power law form.
Okay.
And then the second part.
Like of a hardening situation.
Yeah.
Here we go. Yeah, I don't know. I don't have the model, but it's a model like that. Thank you, Rahul. Yeah.
Thanks, Prof.
Those are permanent deformation models, right? You know, they're available, and they use that one. And again, is with the number of repetitions, right? That you're going to have in a particular amount of time. That's how you fail the soil for that. I don't know much about that one. Good questions. Any other questions that you may have in here? All right, so you need to study for the exam tonight. Okay, you need to study for the exam tonight. Any other questions? All right. All right, guys, so class is dismissed. Thank you very much for your attention. We'll see you then tomorrow.